Chennupati Jagadish from the Research School of Physics, Australian National University, Canberra, who will be conducting today's masterclass to today's event. Thank you very much, Professor. So also on behalf of the organizers, ISSS, PS University, CMTI and IISc, we welcome our speaker as well as all the participants and also the representatives from the organizing committees here to this special class. As mentioned by Professor Suresh, this is the third of the master classes that we have been having this month. We had one on 17th, the 19th, 21st, and today is the 24th. As I mentioned earlier, this was earlier. All master classes were part of the international conference that ISSS used to organize every 2 years. But last year, even though we had announced the international conference, but we couldn't hold it. And we are not really sure now when we are going to hold that. The things look very vague right at the moment. But hopefully things will clear and maybe next year should be able to hold that. But we thought we will go ahead with the master classes because as this will be very useful to particularly the younger students, younger faculty and younger engineers in R&D institutions and industry. So we decided to go ahead and we have been having these classes and I fairly well attended and I'm glad that it's going on well. Um, we've been requesting Professor Jagadish for this, and he has kindly agreed that he will, in spite of his many other commitments all over the world, he has kindly agreed to do this. I think it's what's the time now, sir, in Australia? It's 2:30.
2:30. Yes, thank you, Dr.
2:30. So it's in the afternoon. Anyway, right time for him as well as for us here in India, 10 o'clock. So we look forward to a very interesting lecture today because this is a very specialized topic, so particularly in the area of photonics. There are not too many people working in this country, and I do hope that this masterclass will spur some more people to join and start working in this special area, particularly in terms of research as well as in the industry, because there are a lot of possibilities, a lot of avenues for exploitation of this particular area. So I really look forward to an interesting lecture. Thank you very much again for joining and we may go ahead. Sunil, can you please introduce the speaker and let start the meeting?
Yeah, sure, sir. Thank you for the wonderful words about yeah. So I welcome our today's uh, masterclass lecture speaker, Dr. Chennupati Jagadish. Professor Jagadish is a distinguished professor and a head of Semiconductor Optoelectronics and Nanotechnology Group in the Research School of Physics, Australian National University. He is currently serving as a past president of IEEE Photonics Society. Professor Jagadish is the editor-in-chief of Applied Physics Reviews, editor of 3 book series, and serves on editorial boards of 19 other journals. He has published more than 960 research papers, holds 5 US patents, co-authored a book, co-edited 15 books, and edited 12 conference proceedings and 18 special issues of journals. He is a fellow of 11 science and engineering academics of various countries like US, Australia, Europe, and India, and 14 professional societies. He received many awards, including IEEE Pioneer Award in Nanotechnology, IEEE Photonics Society Engineering Achievement Award, OSA Nick Holyoke Jr. Award, IUMRS Somya Award, UNESCO Medal for his significant contributions in the development of nanoscience and nanotechnologies. He has also achieved Lyell Medal from Australian Academy of Science for his contributions to the physics. He has received Australia's highest civilian honour, AC, a companion of the Order of Australia for his contributions to physics and engineering and in specific nanotechnology. So on behalf of IEEE, I once again welcome Professor Jagadish and the floor is yours, sir. Yeah, thank you.
Thank you very much, Dr. Suresh, for that kind introduction. And I would like to also take this opportunity to thank Dr. Upadhyaya and also all my colleagues from IEEE and also that PS University and IESC and Dr. Gopal Hegde and Dr. Sunil, Dr. Revati, and all of the people, those are involved in organizing these master classes. And I really appreciate for your efforts and really educating and then inspiring the next generation of scientists and engineers. And it's a really pleasure and honor for me to speak to all of you today. In this masterclass, and I'll be covering initially the introductory part of this field, and then later on I'll go and then really talk about the research. And in between, we'll have a few minutes of break where we can have Q&A for the first part, and then we'll come back and then do the second part. So the really photonics, and what is photonics? And so really this is something is worthwhile for us to really think about. And the photonics is essentially the science and technology of generation and manipulation and detection of light. So that's sort of, it's a broadest title which I could give. So that means it can cover a broad spectrum of technologies within the field of photonics. Before I proceed further, I would like to take this opportunity to thank my colleagues, Professor M.R. Shenoy from IIT Delhi, and Professor Ho Tan, my colleague at the ANU, and Professor Sebastian Ludedas from KTH in Stockholm for sharing their slides with me, particularly the first part of the talk, and I really borrowed those slides from my colleagues. And then I want to sincerely thank them for generosity in terms of sharing their slides with me. So here is going to be the overview of my talk, and I'll be really talking in the first part, the introduction to optoelectronic devices. And I've also been asked if I could really cover some aspects of silicon photonics, which I will try to do. And then we'll stop and then take a break and then come back to the second part.
Sorry to interrupt. I think slide is not moving over. Or
Oh,
you're
I
not
see.
moving.
Yes, sir. Slides
It's
are
not
not.
moving?
Not moving.
Oh, okay. So there's something wrong. Sorry. Thank you for letting me know. And
We'll make it full screen and then it will
that's
move.
what I've done. And so I don't know why that's earlier I've shown that. Okay, let me do one thing. Let me reload and then see whether it works. I'll stop this one.
Yeah.
And so then let me see whether I could.
Now it is coming.
It's coming. Okay. And
okay.
so can you still see the screen?
No.
No, you'll have to reload it now.
Yeah, I know. I'm going to do that. Okay, let me see. Okay, then this one and a window, and so let me see where it shows. Oh. Share. So now I'm putting this one. So let me see. Can you see this one?
Yes, sir. It's now visible.
Okay. Now is it moving?
No, sir. It's not moving.
Oh, whoa. Okay. So
if I may, sir.
Yeah,
It
please.
moved last time. Yeah.
Pardon me?
If I may, sir, to allow for presentations to take place, you need to share your entire screen and not just one window.
Oh, I see. Okay. So that's a sort of, because see, I don't normally use Google Meet that much. Mostly I'm using Zoom. And every time I try to use Google Meet, I have had some issue or the other. Let me try the entire screen and then see. Let's hope it works. And so then let me share this one now. And so is it looking okay? No? Okay. It seems to be trying to do. You are presenting your screen.
Now slides coming.
Yeah.
Okay. And so now let me see whether are they move. Okay.
No.
It's moving. No.
Yeah, it's moving.
Yeah,
okay.
It's moving. Yeah.
Okay.
But
That's good. So, but it's not in the presenter mode. It's normal mode.
No. It is not in the presenter mode.
Okay, that's good. Okay, good. Okay. So here's the overview of my talk, and can you see the part 1 and part 2 now?
Yes, sir.
Yeah.
Okay, that's good. Okay, thank you. And I apologize that these technical problems. Google Meet has always been an issue for me. Anyway, so in the first part, I'll be talking about the introduction to optoelectronic devices, and then also silicon photonics. And then we'll stop and have a question and answers, and then after a break, and then we'll come back, and then really part 2 will be the most recent advanced research which we are doing in my group in terms of developing semiconductor nanostructures for optoelectronics and energy neuroscience applications. So as I mentioned that some of these slides, I've borrowed them from Professor M.R. Shenoy from IIT Delhi because of the fact that we both gave a back-to-back lectures, and he gave the introductory part, and then afterwards I gave the research part. So I thought instead of reinventing the wheel, I might as well borrow those slides and then be able to share those things with you. And so then he's really mainly focused on the semiconductor optoelectronic devices. So what is optoelectronics? And optoelectronics is essentially the bringing the optics and electronics together. Conversion of light into electricity, for example, the using photodetectors or solar cells, or conversion of electricity into light, like light emitting diodes and lasers, which I will come back and then talk about. So in terms of means again, these optoelectronics or photonics has been taught as part of the optical engineering or science and engineering or interdisciplinary field as well. And so the optoelectronic devices are widely used in optical communication systems and signal processing and for a wide variety of applications. So some of the optoelectronic devices are light emitting diodes, and then all of us are using LEDs these days, and also laser diodes. And then again, we are using lasers. And in fact, I'm able to speak to you because of the fact that light has been, signals from my computer have been transmitted through light, through optical fibers, and then be able to really convert that one back into electricity using photodetectors. I'll briefly mention about quantum well, quantum wire, quantum dot lasers, and then talk about photodetectors, and then electro-absorption modulators, and then there are many devices like quantum cascade lasers and detectors and others. I'll not be able to cover all the topics, and they all form into the so-called optoelectronic devices. So in terms of this particular part of the talk, and then I'll start talking about the semiconductor optoelectronic materials first, because materials play an important role in order to be able to make any device. And I'll talk about semiconductor heterostructures and double heterostructure lasers and some other kind of high frequency, single frequency lasers, and then light emitting diodes, and finish off with the photodetectors. So in fact, Professor Shenoy has given a full video course of 46 lectures, and I understand that they're available on YouTube, and then you can go to NPTEL site and then be able to really download these things and be able to listen to. Or otherwise, if you simply Google his name, and then you'll find the link and then be able to listen to those ones. And really, what I'm talking about, the first part is really a summary of what he has covered in 46 lectures or so in an hour or so. So that's why I need to be brief. And then if you really want to know more details, feel free to really go and then listen to those lectures. So before I proceed further, and then let's talk about world at night. And then again, when we talk about light, and then again, the light emitting diodes are really playing an important role. And then you can see that this is a composite picture created by the NASA. And then you can see that there's a lot of energy being used in US, for example, for lighting applications, and in Europe, and India, and then China, and then Japan, and Australia, and where we got mostly people at the coastal regions of the country, and that's why you see most of the lights there. So in the US alone, about 20% of the electricity is used for lighting applications. And if you can really save the energy usage by using LED lights in place of the incandescent lamps which we're using, you can really save for each percentage of reduction of the energy usage. And then you won't be needing about 1 gigawatt or 5 gigawatt or 1 gigawatt or watt power plants, so that you can see that how we can be able to significantly reduce the greenhouse gas emissions using these LED lights rather than the incandescent lamps or Edison lamps which we are used to using in the past. So here's an example of the light, and in fact, the lighting revolution, which has started a revolution. And then we initially started off with burning oil or wood, for example, for light, and then later on we've gone for gas or kerosene. And then we got into the electricity came, and we gone into incandescent lamps. And the incandescent lamps, the efficiency has not gone up by more than 5% or so. Then fluorescent lamps came up, and then we call it as tube lights or compact fluoros, and they typically have got 25% efficiency or so. But whereas the LED technology, which has been developed during the last 20 years, has really led to significant enhancements of the efficiency of the LEDs, and particularly the development of the gallium nitride technology, and leading to efficiencies now close to 50% or so. So really, if you go from 5% efficiency of the incandescent lamps to 50%, you'll be reducing about a factor of 10 of the reduction of the energy costs, and that's where the attraction is in terms of being able to use these LED lights. And again, semiconductor development played an important role. But again, lasers, and then we are all using lasers. For example, if you're using a CD player or a DVD player or a Blu-ray player, and depending on what player you're using different colors of light of different wavelengths. And then, of course, smaller the wavelength of light, and you're able to pack more information. So that's why you're using these lasers and, of course, DVD players and others which we have been using for a long time. And then again, in terms of optical links and the optical communications, for example, and then as I mentioned earlier today, and the signals from my computer are been be converted into light signals by using lasers, and they use modulators, essentially the on-off switches, and then you send information to the optical fiber, and then after the on the other end in India, for example, and then you are really converting that light signal into electrical signal using photoreceivers, or essentially photodetectors, which are converting to electrical signals, and that's how you're able to listen to. And in these optical fiber systems, there are also some amplifiers which they use. There's optical fiber amplifiers and other things. They're all part of the photonics technology, for example. Instead of using a single wavelength of light, and you can use a multi wavelengths of light, and then you can do the multiplexing and then send through the fiber, and then other side you do the demultiplexing. So because optical fibers have got a huge bandwidth, so that means you want to make use of that bandwidth rather than sending single color of light. And then typically these days you send about 32 wavelengths of light simultaneously, or 64 wavelengths, so thereby you're exploiting large bandwidth of the optical fibers, and then you're able to really send large amounts of information. And typical transmission rate is about 40 gigabits per second or so. People are moving towards hundreds of gigabits and other things, and wide variety of technologies being developed, including lasers and modulators and multiplexers and demultiplexers and receivers and various things. So really, all these technologies are playing an important role in our day-to-day life. For example, if you're using internet, invariably you're using photonics and optoelectronics and optical fibers and wide variety of optoelectronic devices. So again, if you are using these semiconductor devices, photodetectors, which I was mentioning to you, for example, if you use infrared detectors for doing medical imaging applications, where if you really create some damage to your muscles, and then you cannot see it, but whereas you use infrared image, and you'll be able to clearly see that one. So they can be used also for night vision applications, and then, for example, if you're able to see them in the night, again, either in the for example, defense personnel or movement of arm. Movement of various armed things, or otherwise even looking at the deer in this case, which is a NASA picture. Also, they're used in manufacturing, for example, is infrared detectors. And there, for example, if you can be able to go and image a computer chip and be able to identify while you're operating it where the heat is generated, so that the computer chip designers are able to redistribute the circuits so that you can minimize the amount of heat generated, because heat dissipation is a major issue in terms of computer chips these days, because you're making a packing large number of transistors. As many of you might have heard that recently, IBM and others have demonstrated a 2 nanometer. The node, otherwise 2 nanometer, is the smallest feature in a transistor. So that means you're able to meet tens of billions of transistors in a square inch of silicon, for example. And also these days, nowadays, people are using concentrated photovoltaic systems. We are using 3-5 multi-junction solar cells, which are exceeding efficiencies. In fact, now 47% or so, which are used in these concentrated systems, which have been developed for the space applications. But now people are exploring how to make use of them in the terrestrial applications as well, which I'll come back. So now let me move towards the semiconductor materials. And if you go and look at the periodic table, and then silicon is the workhorse for the microelectronics industry. And so typically, basically it is used widely if you're using any smart device, and most likely you're using a silicon device because of the fact that it's the workhorse for the microelectronics industry or nanoelectronics industry, for example. And of course, germanium is also used, and combination of silicon germanium has been used for electronics applications, for example. But unfortunately, silicon is not a good light emitter because it's an indirect band gap semiconductor, and that's where we end up looking at other materials of the group 3 of the periodic table, and aluminum and gallium and indium, and then group 5 of the periodic table of the gallium and the phosphorus and arsenic antimony. And you can choose a combination of the materials of the gallium arsenide or aluminum, gallium phosphide, indium phosphide, gallium antimonide, and then wide variety of materials. And the nitrides have been not listed here. And of course, you can make also gallium nitride, indium nitride, aluminum nitride as well. Those are the ones which have been used for the LED applications, for example. So, okay. Also, you got 2,6 materials which are used, for example, zinc oxide, and oxygen is also missing in this one. And then again, cadmium telluride, zinc telluride, mercury telluride and mercury cadmium telluride particularly is an important semiconductor for infrared detector applications. And nowadays, cadmium sulfide and cadmium telluride based solar cells have been widely used, and including also indium, means copper, indium, gallium, selenide, and wide variety of materials is used for solar cell applications and other things. So when we're talking about semiconductors, we always talk about the conduction band and the valence band, and essentially conduction band, the bottom of the conduction band and the top of the valence band, which will determine the band gap of the semiconductor. And if you go and look at this energy gap, energy profile of this one in the K space, and then essentially momentum space, and then essentially what you see is the EK diagram, and then what you see is this nice parabolic type, the conduction band, and then also the valence band here. And again, the minimum in the conduction band, the maximum in the valence band will determine the band gap of the semiconductor. But whenever you call as a direct band gap semiconductor, indirect band gap semiconductor, so whenever you got the minimum in the conduction band and the maximum in the valence band is taking place at the same wave vector or the same momentum value, and then that's where we call it as a direct band gap semiconductor, where you excite the electrons from the bottom of the conduction, from the top of the valence band to the bottom of the conduction band, and then the electrons fall down and emit light. It's a direct process, so that's why you end up having direct band gap semiconductors. So this is typically like gallium arsenide, indium phosphide, gallium nitride, indium nitride. They're all direct band gap semiconductors. So in the case of indirect band gap semiconductors, which I was mentioning about silicon, so in this case, what happens is that the bottom of the conduction band is at the different k value or the momentum value k wave vector, or the top of the valence band is at a different point. So that means if you really have to really excite these electrons, and then you need to have a phonon to be able to really couple this one into this particular state, because you want to conserve both the energy and the momentum. And then that means, it's a really inefficient process of light emission. You need to be able to generate photon, as well as need to have a phonon in order to be able to, phonon is a lattice vibration, in order to be able to generate photons. So that's why silicon is not widely used as the light emitting material, for example, for lasers or LEDs and other things. Though most recently people are exploring, instead of using a cubic silicon, but using silicon germanium, which is wood sides, hexagonal structures, and you can make them as also direct band gap. That's most research is going on, and that's an exciting development in this area as well. So whenever you look at these semiconductors, and then what we do is that we look at the band gap of the semiconductor and its lattice constant, and the water type of colors of light which has been emitted by these ones. And you can see gallium arsenide is here, aluminum arsenide is there, and then indium arsenide is here, indium phosphide is there. And as you can see that the different semiconductors have got different band gaps on the y-axis, and on the x-axis you got a different lattice parameters. What is a lattice parameter? Lattice parameter is a unit cell of the crystal which is repeating itself in a crystal in all three dimensions, for example. So ideally, what you want to have is that you want to have the lattice matching of the layers, whereby you'll be able to combine these ones and then be able to really create them, be able to tune the band gap of these semiconductors, which I will come back to. For example, the cases where I am really connecting these ones, this dashed line, and this slide is particularly from Professor Ho Tan. And you can see that aluminum arsenide is not a direct band gap semiconductor. So not all the compound semiconductors are direct band gap semiconductors. Some are and some are not. And then you can also see that aluminum arsenide has got a very close lattice constant as gallium arsenide. So that's why you can be able to really tune the band gap of the semiconductor here by mixing the aluminum and gallium and arsenic. So basically you can really tune the band gap, and that really gives you a lot of flexibility. So that means you can be able to emit the colors, different colors of light, for example. Whereas in the case of indium phosphide, and then you can see that indium gallium arsenide is a particular composition of indium to gallium ratio of indium gallium arsenide with 53% of indium is lattice matched to indium phosphide. It becomes easier if it is making the lattice match structures. And if you really try to deposit a material from one on the other of the different lattice constants, you essentially create a lot of strain. And beyond a particular thickness of that particular layer, what you end up having is a dislocation formation and other things. So then it becomes useless as far as optoelectronic devices are concerned. Okay. So here is a case where I plotted, again, this is Professor Chennai's slide, and you can see that whenever you see the name of Professor Chennai's name, and then that you know that this is a slide from Professor Chennai. You can see he's plotted like silicon and germanium. These are the two indirect band gap semiconductors. What is the band gap and what is expected light emission? And sometimes it's weak, but still it can emit light, but it's a very, very weak light emission. So the direct band gap semiconductors like gallium arsenide, indium arsenide, indium phosphide, aluminum arsenide is indirect, and gallium phosphide is also indirect, for example. And you can see if you go to the indium arsenide, for example, you can go to the infrared regions of the wavelength of light. And again, gallium antimonide goes also infrared region of the spectrum. Indium antimonide goes to the infrared region of the spectrum as well. So really, depending on what is the wavelength of light you want to emit, or what's the wavelength of light you want to detect, you choose the right band gap semiconductor so that you'll be able to really use them for a wide variety of applications. So here is an example of the case where I was mentioning to you, by mixing the materials, so-called alloy semiconductors, and then you'll be able to really tune the band gap. So you can see that the gallium arsenide is here, aluminum arsenide is here, and then the direct band gap of the semiconductor is plotted here, for example. So you can see that the gallium arsenide case, the direct band gap means the maximum in the valence band and the minimum in the conduction band is happening at the same wave vector, and that means then you're really talking about this is direct band gap here, for example. I also told you that the aluminum arsenide is an indirect band gap semiconductor, so that means the bottom in the valence band is taking place at a different wave vector. In the conduction band is taking place at the different wave vector than the top of the valence band. So while you're mixing up to certain point of the aluminum gallium arsenide, about 40% or so, you keep this semiconductor direct, and then afterwards it becomes indirect. So that means up to this point, you can be able to use this semiconductor for light emission applications, for example, because they all will be emitting efficient light. So what will happen if you got a material which you got a large lattice mismatch? So that means unit cell of the one crystal is different than the other crystal. So I'm just showing you the block of this one. This is a slide which I borrowed from Professor Hotan. And you got a layer which you don't deposit. We call it as epitaxial layers because they try to really mimic the substrate layer, substrate which you're using. And you can see here the substrate has got same lattice constant as that of the epi layer. That means they really nicely, it grows, there's no issue, there's no dislocation formation or anything of that sort. But whereas if you got a layer which you're depositing, which has got a large lattice constant with respect to the substrate, and then it has to compress itself and then distort itself in a tetrahedral distortion in order to be able to accommodate the same lattice constant as that of the substrate which you're starting with. It keeps growing, and of course, it doesn't like to really being distorted, and you exceed the elastic to plastic transition limit, strain limit, then what happens is it starts relaxing back to its original lattice constants, and that's where you end up creating dislocations and defects. And those dislocations are really acting at non-radiative recombination centers. So it means they won't light is not going to get very efficient light is not going to come out of that. But also that if you got a material which got a smaller lattice constant with respect to the substrate, it expands, and again you create a tetrahedral distortion here, and then it can grow up to certain layers and beyond certain thickness, which we call it as a critical layer thickness, and it relaxes back to its original lattice constant. Again, it creates dislocations. So you can make use of this compressive and tensile strain up to certain point, and then also strain also modifies the band gap of the semiconductors, which we also exploit, for example. So here is a case where indium gallium arsenide, which has got a lattice mismatch with respect to gallium arsenide. And this slide, what it plots is a critical layer thickness. What is the amount of layer of the thickness which doesn't dislocate or relaxes back to its original lattice constant, is very much dependent on the indium composition, because the higher the indium composition, higher the strain you're introducing. As you can see that the higher the amount of strain you're introducing or higher indium concentrations, the thickness of the layer becomes very, very small. So that means you really cannot make a very, very thick layers. I'm plotting here also in angstroms. So now you're talking about a few nanometers and beyond which it starts dislocating sort of thing. So that's why as long as you make those layers below the critical layer thickness, and then you'll be able to make these strained layers. So why are we interested in strained layers? Most interestingly, and if you really, this again, it shows the critical layer thickness, and then if you exceed that one, you create the dislocations. That means dislocations are nothing but missing atoms or excess atoms, depending on what you're really looking at, for example. So here's a case where if you do not have any strain, and you got the bottom, the conduction band is looking here, and then you got the valence band also has got a heavy hole and light hole, you can see here. But once you introduce the compressive strain, then what happens is that you lift the degeneracy between the heavy hole and the light hole, and then also increase the band gap of the semiconductor. So now you can see that instead of only alloying the semiconductors and tuning the band gap, stain also could be exploited, be able to tune the band gap as well. And if it is a tensile stain material, again, it reduces the band gap. And again, you see light hole is on the top now, and here the heavy hole is the top, and that changes the polarization properties of the the lasers, the materials, light emission, and you can be able to make compressively stained lasers or tensile stained lasers as long as you stay within the critical the dimension of the critical thickness below that one. So now if I really look at the optoelectronic devices, and then as you know that I was talking about LEDs and lasers, and then basically LEDs and lasers are both are the diodes, a PN junction diode, and a photodetector is also a PN junction diode. So in the case of LEDs and lasers, and essentially what you do is that you connect to a power supply, and then you forward bias that. So that means P terminal of the diode is connected to the positive terminal of the battery, and then the negative terminal of the diode is connected to the negative terminal of the battery. So that means you're essentially forward biasing the diode, and you're injecting current essentially and getting the light out of that one. The same thing also happens in the case of LEDs, laser diodes. But only difference between the LEDs and lasers is that the light emission is happening in phase with each other, but whereas this light emission is not of the wave light photons have got really have got scattering in all directions, and more importantly, they don't have any clear phase relationship. So that's why we call this as an incoherent light, and because of the fact that there is the phase relationship here, we call it as a coherent light. In the case of photodetectors, we shine the light and collect the electron hole pairs. So that's why you end up reverse biasing this diode. So thereby you're able to efficiently collect the carriers so that you can be able to measure the current. And then that will give you the power of the light which has been falling on this one, and the wavelength of the light, and various things, for example. Excuse me. So the semiconductor lasers have been invented a long time back in 1962 or so. And so really close to 60 years back, and then various groups, 4 groups simultaneously have really demonstrated these ones from IBM and Bell Labs and the GE Research Labs and various groups, for example. Why are you interested in semiconductor lasers? Generally, they are compact and efficient, and you can modulate, or that means on and off, that means you can send information, and you can also integrate multiple lasers into optoelectronic device integration. So that's why people are very much interested in really using these semiconductor lasers for a wide variety of applications, whether I talk about optical communications or DVD players or CD players or laser pointers, and wide variety of applications. Lasers are used these days. This compactness and the highly efficiency and low power consumption, all of them really played an important role during the last 60 years. And then we can never imagine that today that our modern life can live without the lasers and LEDs, for example. So what will happen in the case of this laser? And then so you can see that you create a PN junction, and that means you dope the semiconductor with the top one is a P-type dopant and the N-type dopant. For example, in the case of gallium arsenide or indium phosphide, and the both are direct band gap semiconductors. For P-type doping, either we put the zinc or beryllium. If you're using MOCVD growth, metal organic chemical vapor deposition, you typically use zinc. If you're using molecular beam epitaxy, you use beryllium. They both come from the group 2 of the periodic table. So that means you got one missing electrons, and that's where you create the P-type or holes and the positively charged part of the semiconductor, for example. The N type of the semiconductor, what you do is that you dope this one with silicon typically, or tin, for example. Silicon is from the group 4 of the periodic table. So that means it replaces silicon, gallium or indium, and it's got an excess electron. That's where you put the negative type and the N type semiconductor. And then these both have got a metallurgical contact between both of them, where you deposit one on top of the other with a different dopants, and then you'll be able to make a PN junction. And then you make some contacts and inject current and look at the light coming out of these ones. And also the facets which you really created, the crystal facets or the cleaved facets and other things really are going to play an important role, which I will come back to and talk about. Again, in the lasers and LEDs, they're forward biased because the P-type is connected to the positive terminal, and N-type of the semiconductor is connected to the N-type terminal. Excuse me. So here is a case where you can see that the more details of this particular semiconductor laser, and instead of just having N-type and P-type semiconductor, and then you got something called an active layer. And so then also you really try to create a waveguide here, and then try to put some silicon dioxide, a dielectric layer, put some metal and then selectively inject carriers from the top, and then of course the bottom you make a contact as well. So thereby you're able to inject carriers and be able to guide the light along this particular waveguide, which really allows to be able to really make the laser to work. And again, the doping is really important to reduce the electrical resistance of the device and also being able to make good low resistance ohmic contacts. If you do not have that one, what happens is that you're really trying to inject current and then you really got a large resistance at this interface here. So that means what will happen is that, means you're creating a lot of heat, and then the heat really pulls the gain down, then it becomes a vicious circle. So that's why low resistance contacts and also highly doped semiconductors play an important role, for example. So then, of course, we move towards from just lasers to heterostructures. Heterostructure lasers really played an important role. And then essentially, in the case of a standard laser diode, what you want to have a gain medium and a resonator. And by cleaving the semiconductor, what you can do is that you can create mirrors at the both ends of the nanowire, and there's a longitudinal cross section here along the length of the semiconductor laser. And so again, you get a P-type gallium arsenide, P-type aluminum gallium arsenide, which has got a larger band gap, which really provides essentially electron confinement and optical confinement within this pink region here. And you got N-type aluminum gallium arsenide and N-type gallium arsenide. I told you aluminum gallium arsenide has got a larger band gap than gallium arsenide, so that allows you to be able to confine the light and the electrons here, for example. Okay. So then, of course, if you're injecting current, the light is bouncing back and forth, and if you exceed the losses, gain exceeds the losses, and then the light starts coming out and also in phase with each other. So in terms of, originally people started looking at homojunctions. Homojunction means you take gallium arsenide or silicon or indium phosphide, you dope this one N and P. That means the same type of material used for both both sides of this junction, for example. In the case of heterojunction, and we are creating a gallium arsenide or aluminum gallium arsenide, and that means two different semiconductors. So because they're different materials, they're called as a heterojunction, for example. So also, in fact, the development of the double heterostructure really played an important role for this optical confinement and electron confinement here by putting this P-type in aluminum gallium arsenide and N-type aluminum gallium arsenide, because they got a low refractive index and higher band gap that allows you to be able to really both create a potential barrier and also the optical barrier, because of this light likes to be in the larger refractive index medium, for example. So in fact, the development of this introduction of these heterostructures and also particularly double heterostructures and how they are useful for transistors as also for lasers and other devices. And then Professor Zoris Alfarov, and then from Yoffe Institute in St. Petersburg in Russia, and Professor Herbert Kromer, who was at University of California, Santa Barbara, and they both won the Nobel Prize in Physics in 2000 or so, because of the fact that it's really revolutionized information and communications technology, these particular double heterostructure lasers and double heterostructure, the transistors, high electron mobility transistors, heterojunction bipolar transistors, and others really played an important role in high-speed electronics as well as optoelectronics, for example. Okay. So why heterostructures? And I mentioned to you carrier confinement, and carrier confinement is something which is because of the fact that you got a larger band gap material and is surrounding the smaller band gap material. That means there's a potential barrier. Carriers cannot go up or down, and they have to recombine within this pink region, for example. Here. Optical confinement comes from the refractive index difference, and again also creates low optical losses as well. And then it also provides design flexibility and other things. And then of course nowadays there are no lasers or LEDs typically used with the homojunctions. All of them are making use of the heterostructures and also the double heterostructures as well. Of course, there are very much of a complex devices and other things, and which I would not be really going into details of those ones, for example. So here is a case where PN junctions, and so then again homojunction, and I won't go into the details of those ones, and I've already mentioned these ones to you. So what will happen if you really have got a P-type and an N-type materials and you bring them together? For example, here's a case where a P-type semiconductor, you got the Fermi level is the close to the valence band, because it's the holes are dominant here, because the conduction carriers are majority carriers are holes here. In the case of N-type semiconductor, and then you got the Fermi level is closer to the conduction band, and then the majority of the carriers are the electrons in this case before contact. But if you bring those two together, what happens is that, and essentially what you're doing is that the Fermi level gets readjusted, and then essentially band bending takes place. And then because Fermi level want to be in the same level in both the materials, so in the process you end up creating this band bending and leading to this so-called PN junction, where you got a p-type holes here and then n-type electrons in this part, and you create something called a depletion region, where the electrons holes have recombined and creating a so-called depletion region, for example. So whenever you forward bias these ones, and what happens is that the band bending changes, and also the end up creating so-called these quasi Fermi levels. And then so instead of having a single Fermi level which is covering both n and type here, and then what you end up having is a quasi Fermi level for the holes here, quasi Fermi level for electrons. So that means you end up having a large concentrations of electrons here, large concentrations of holes here, and then they recombine and then end up creating electron hole pairs, recombining and generating light, for example, particularly if they're using the direct band gap semiconductors, for example. I won't go into the details of these ones, and so essentially the Professor Shenoy really talks about the number of carriers and then how that is dependent on the density of states in the conduction band, and also Fermi level position with respect to the conduction band, also the temperature of the device. And then as in the case of p-type, again the valence band states, and then the valence band edge minus the effect, the Fermi level of this particular holes, for example, here. In thermal equilibrium, essentially the NP is equal to the essentially Ni square. Ni is the intrinsic value of the semiconductor, intrinsic carrier concentration of a semiconductor. So that's what happens in thermal equilibrium. Because in the case of the quasi-equilibrium, which you're creating in the case of forward biasing the device, for example, and then they end up behaving quite differently, because you end up having the so-called the quasi-Fermi level for electrons and quasi-Fermi level for holes. So in the process, its NP is equal to the electrons and holes multiplied is equal to not just Ni square, it also is dependent on the quasi-Fermi levels, and that really plays an important role. And that's something which you need to be aware of when you're dealing with these forward bias devices, for example. So here is a case where if you got a heterostructure, for example, here is got a larger band gap material, and then on both ends, and then you got the smaller band gap material, and if you bring them together, and then again the Fermi level alignment takes place, now you can see that you're really creating mostly the holes are here, p-type region, and the whole electrons are here. And then now you can forward bias these things, for example. So then essentially this again you create the quasi-Fermi levels, and then the electrons are injected to this region where the smaller band gap material holes are injected here. But also because of this barrier height here, electrons cannot go that way and the holes cannot go this way. That means you create a barrier for electrons and holes. That's where they end up recombining very efficiently. So that's what Professor Zaro Salfarov and Professor Herbert Kromer has demonstrated their Nobel Prize winning work. And that's why double heterostructure lasers are much more efficient than the homojunction lasers. Initially, when the first lasers have been demonstrated, homojunction lasers were all operating at room temperature, low temperature. And then when the heterojunction lasers are the ones which they need to use in order to be able to really get the good carrier confinement and optical confinement, leading to excellent performance and room temperature operation of these wide variety of the lasers, so for example. So again, this gives you the details of the, how the longitudinal cross section of this particular device, and then again, p-type gallium arsenide, p-type aluminum gallium arsenide, n-type aluminum gallium arsenide, and n-type gallium arsenide, and the light is propagating here. And then again, because of the fact that the gallium arsenide has got a smaller the band gap, it also has got a larger refractive index, and that's how the optical confinement has been created here, for example, here, and then I'm showing the other way around. And then this optical mode profile looks like that because of these differences in the refractive index between the gallium arsenide and aluminum gallium arsenide, for example. That really allows you to be able to keep the light in a particular area, really be able to create the waveguide and be able to really allow the light to bounce back and forth, for example. So again, of course, if you really want to talk about laser diodes, and you need to have a gain medium, and then again, the semiconductor acts like a gain medium. And then by really cleaving both ends of the both ends of this particular semiconductor structure, double heterostructure structure, essentially you're creating like a resonator because of the refractive index difference between the semiconductor, 3.4 or so, and then the air, which is about 1, and then light bounces back and forth, and they create two mirrors, and essentially without having to do anything, and you create mirrors on both ends, and then that acts like a resonant cavity, for example. I've already talked about wide variety of semiconductors, and I was mentioning about indium gallium arsenide earlier. And then by really choosing this particular composition, you can be able to make the lattice matching of this particular structure. So that really plays an important role. And then you can be able to choose what materials are really appropriate, for example. For example, gallium arsenide lattice constant is very close to germanium. So that's why these multi-junction solar cells are grown on germanium substrates, for example, here. Silicon is lattice matched to gallium phosphide, and then people end up going the gallium phosphide as a buffer and then try to gradually change the composition, so thereby can minimize the dislocation formation and other things. So again, I've already shown this one to you, and so really essentially saying that this is the waveguide here, and then this is the way the light is coming, and you're injecting the current and the p-type holes and electrons from here, and then the light is propagating like this, and then where the recombination of this electron hole pairs are generating leading to the laser. So if you go and look at the particular materials, and depending on the what material you're using, and you end up getting different operating wavelengths. And then again, also this is a case where output power of a laser diode with respect to the injected current. And then you can see that below the threshold, for example, you end up getting very low amounts of current light. And they essentially a spontaneous emission which has been coming, and essentially they're acting like light emitting diodes. And above the threshold, they're acting like a coherent light sources, like a laser diodes. And you can see very much of a linear power increase is taking place above threshold. So very efficient light emission, for example. But also this is very much dependent on the temperature of the device as well. If you go to the higher the temperature and the threshold current is higher, and then of course if you're going higher to the higher temperatures and again threshold current increases, also gain saturation starts taking place because of the fact that the heat generation really pulls down the gain, peak of the gain, and becomes a challenging task. And that's where what you want to have is a highly efficient the lasers which have got very small changes in the threshold current with respect to the temperature, which really provided by the quantum dots, for example. So that's why in the recent years, and then people have been focusing on from quantum wells to quantum nanowires and quantum dots and other things. And we call it as something called a characteristic temperature as a T naught, and that's what essentially is determining is that what is the temperature, the characteristic temperature. That means characteristic temperature is determined, and then how much of means how this threshold current is going to change, and then the higher the characteristic temperature, the change in the wavelength and also threshold current becomes reduced as well. You can see the gallium arsenide, aluminum gallium arsenide has got a higher characteristic temperature than indium phosphide, indium gallium arsenide phosphide, because of this the so-called the band discontinuities between the smaller band gap material and the larger band gap material. Those band discontinuities are smaller in the case of indium phosphide structures than gallium arsenide. So that's why you end up having higher T naught, for example. So that means these lasers which are operating from the gallium arsenide structures will be much more thermally stable than the indium phosphide ones. Probably that's a takeaway message for you. And again, depending on, you can really get these days, in fact, even watts and watts of power from these individual devices, for example. And again, depending on what wavelength of lasers you want, you choose a right kind of the semiconductor and also right kind of substrate, which is lattice matching, or with only a small amount of strain you can introduce and be able to do that, for example. So in fact, this is Professor Shenoy's group, and where he is really showing the so-called you create a multiple longitudinal modes because of the fact that you got a laser cavity and then the light is bouncing and back and forth, and they'll be able to really create essentially a Fabry-Perot cavity, and then multiple modes can be supported by the Fabry-Perot cavity, and then you can in fact be able to measure that one in an optical spectrum analyzer or using an spectrometer, depending on what you've got here. You can see that there are multiple longitudinal modes that are operating. For some applications is okay, multi-mode devices, because high power lasers where you're using for machining and other things, they're okay. But if you want to really send information through optical fibers and other things, people prefer to have single mode devices, and that's where we'll come to and then be able to talk about, for example. In order to be able to get a single optical mode or longitudinal mode, what people have introduced is some sort of a grating, this so-called distributed feedback laser. And then essentially what you do is that this reflector has been not a single one, but it's been distributed. So that's why it's called a distributed feedback laser. So what happens is that essentially this is something like a grating type structure, which will determine which particular optical mode is going to be supported by that one. All other modes will get extinguished, and then only single mode will be supported, and that's where you call a single longitudinal mode lasers. Particularly for optical communications, they play an important role. So this is a normal Fabry-Perot laser. You get a multiple longitudinal modes. This is a distributed feedback laser, DFB laser, which is in short, shows only one single longitudinal mode laser. So that makes a big difference in terms of being able to really have got a multiple lasers operating at multiple wavelengths, and so thereby you're able to simultaneously send information through optical fibers, for example. So here are some of these the package devices, and again, you want to be able to really use it in the in the field, for example, and people be able to do that one. Here is a 1550 nanometer DFB laser, because 1550 nanometers and 1300 nanometers are the two wavelength regions which are where optical fibers have got the lowest absorption and dispersion. So that's why people typically use 1300 nanometers or 1550 nanometer lasers. And here's an example of the case of a 1300 nanometer laser, and then which is used for telecommunications and access and junction applications. And whereas these 1551s are used for long distance communications, like undersea cables people are using, for example. And these particular devices are mainly one which are probably sending information to you, for example. So here are some of the various laser diode packages, and this is the one which is I showed you earlier. And then also you got something called TiVo cans, and they can also be used, for example, for laser pointers or otherwise DVD players and other things. And the heat dissipation is always an issue. Heat sinking really plays an important role. And also coupling of the light from the laser to the optical fibers is an important issue as well, because there will be typically large amounts of losses takes place here, because of the fact that these Fabry-Perot lasers are any of the edge emitting lasers, because light is coming from the edge of the wafer. So that's why these are called as edge emitting lasers. They typically have got an elliptical shape of this optical mode, and then whereas the shape of this mode of these optical fibers is circular. So that's where you end up creating a lot of losses, and people end up putting some lenses and other things to be able to convert that one to minimize your coupling losses and other things. And that's how you're able to connect it to an optical fiber network or one thing or the other, for example. So because of the fact that now there are lots of complexities of really be able to really make these edge emitting lasers and able to couple the light for optical fibers, people have been thinking about how do you really be able to make the reflectors in the vertical direction rather than these edge emitting lasers on the edges of the semiconductor, for example. So here is a case what people have. Kenichi Iga from Tokyo Institute of Technology has come up with this idea, and so he's really demonstrated how about growing a Bragg mirror, essentially quarter wave plates of two different refractive indexes, so thereby they're reflecting a particular color of light, for example. And then they were able to show that we can really get about 99% efficient, more than 99% efficient distributed Bragg reflectors. And then you put some multi-quantum wells here, and then put another distributed Bragg reflector, but then try to keep the reflectivity of this Bragg mirror a bit lower than this one, so that light is coming in the vertical direction. And again, you try to create a p-type, a p-n junction, and inject current, and then try to look at the light coming out of these ones. So in this case, this aperture will determine the shape of this particular laser mode, and then typically what you end up getting, you get a beautiful circular mode. Also, because of the fact that it's a vertical emitting laser, that means you can really create an array of lasers which are arranged in the two dimensions, and that really opens up a lot of opportunities. For example, if you're using iPhones and other things, and typically they got a facial recognition system, and they're making use of vertical emitting surface emitting lasers. And so those are the ones which are able to really shine light on you and then be able to really see who you are, and then only the phone opens up and other things, the software and other things play an important role. Also, these days, in terms of data communications and other things, people are using VCSELs. The power needed is power generated from these ones are not as high as the edge emitting lasers, but sufficient enough to be able to use it for short data links and other things, data communications and other things. Vertical cavity surface emitting lasers are playing an important role, because the cavity is in the vertical direction. Also, light is coming from the surface, so that's why they're called as a vertical cavity emitting surface emitting lasers. So again, we talked about the double heterostructure lasers, and so just to really give an idea, you got a double heterostructure and a larger band gap material, smaller band gap material being sandwiched here, and then gallium arsenide is typically used in this case, for example, and aluminum gallium arsenide has got a larger band gap here, right? So what will happen if you really reduce the thickness of these smaller band gap materials, sort of thing? So that's where we started moving from bulk materials to quantum wells, quantum wires, and quantum dots. So here is a case where if you got a semiconductor which is in the bulk form, energy as a function, of the density of states as a function of the energy, for example. So essentially, what it's got is a density of states, so the number of states which are available for electrons or holes to occupy. This is the case for electrons, for example, here. And then this typically got a square root dependence of the energy, for example, here in the case of bulk. But if you put a smaller band gap material, this green material between the two larger band gap materials, for example, gallium arsenide here, aluminum gallium arsenide on the other side, you end up changing the density of states. You end up creating this step-like density of states. Now the carriers cannot go anywhere in this direction, but they can move in the two dimensions. And so that's why it's called as a quantum well. Okay. So, but whereas if you really confine the light in the other direction as well, and then only allow the electrons allowed to be able to go in only in one direction, and we call it as a quantum wire. And then again, you can end up this sort of a spike-like density of states, for example, here. And if you confine the electrons in all three dimensions, so it creates a quantum dot or a quantum box, and then essentially you got a discrete energy levels, which is like the atom-like density of states. So that's why sometimes quantum dots are also called as artificial atoms. So in fact, most of the current optoelectronic devices are making use of quantum wells, and some of the devices are making use of quantum wires and also quantum dots. Particularly quantum dots have got a much higher thermal stability and also much higher modulation speed. That means you can switch them on and off faster for higher frequencies. So that's why quantum dot lasers are coming into the market, which is quite significantly. For example, we and others have really worked in this area. And Professor Yasuko Arakawa from Tokyo, Professor Dieter Bimberg from Technical University of Berlin, and Professor Palla Bhattacharya from the University of Michigan, and then and many other groups have been working, and then we have worked on all three types of lasers as well, and also infrared detectors as well. So how does the quantum double heterostructure work, which we talked about? And then you got this smaller band gap material sandwiched between larger band gap material. This itself doesn't act like a quantum well unless otherwise you really bring the thickness of this particular gallium arsenide layer is to smaller thicknesses, and then only create this one. So it created essentially potential well, because electrons or holes which are here, they cannot go to this here because there's a barrier here. That's why it is called as a man-made potential well by Gerard Bestard, as I talked about. Call this as a man-made potential well, sort of creating this well and then the barrier, for example. So now if you go and look at the density of states, for example, if the thickness of this gallium arsenide is about 100 nanometers, so you get many levels here. But if you reduce the thickness of this gallium arsenide to 20 nanometers, it can support also a few more energy levels of the density of states here. But then if you really go to these smaller thicknesses of 4 nanometers, and you can see only the ground state and the excited state, and then that means you're only able to create the electrons are either sitting here or there, for example. So really, this so-called quantum well, which I'm talking about. Okay. Here's a case where now, if I excite the electrons from the valence band to the conduction band, and then they really are sitting here or here, and then they recombine and then emitting light from these ones. And again, that's what happens in typical like quantum well laser, for example. Here, this slide I took it from Professor Hortan, for example. So typically in a laser or infrared detector and other things, we don't use a single quantum well because the volume of the material which you got is very small, and we really try to put a multiple quantum wells, but they are decoupled from each other electronically. So that means the wave function of the electron in this one is here, in this one is here, and this one is here, this one is here. But of course, you can also create the coupled quantum wells and other things that becomes very complex. I won't go into details of those ones. Multi-quantum well allows you to be able to create a large amount of the gain volume, and that means you'll be able to get a much higher output powers from these lasers, and that's why I end up using typically 3 quantum wells or 5 quantum wells, and depending on the particular kind of device design which you end up having. So again, this multi-quantum well laser, and then how the electron wave functions distribute and other things, and Professor the Shanais and his students have really looked at that one quite in detail. So there is something called a quantum confinement effect, and if you take a quantum well, you see the electron wave function here. In this case, for example, I'm only showing the electron wave function, and the whole wave function will be in the other direction. And then if I apply the electric field, what happens is that the band bending takes place, and then this electron wave function starts broadening and also shifting. So that means the absorption wavelength can be changed quite significantly. So thereby this can be used for the modulators, for example, by essentially applying electric field. You're creating a band bending in a quantum well, which changes the peak at which the absorption takes place. By doing that one, you're able to switch on and off and be able to really laser is coming and then going to the modulator, and modulator by electrically switching on and off. So that means you're sending the information using the modulator, and then that can really be able to send high speeds of information, for example. Because sometimes directly modulating lasers beyond certain frequencies, like beyond 40 gigabits per second, now things becomes much more challenging. But modulators, because they can be really be able to modulate it much faster because you keep the laser in a stable state, for example. So let me now move towards light emitting diodes, and then essentially spontaneous emission of a laser is part of the laser is light emitting diode, if you want to really call it that. Again, you got, in this case, you got the PN junction here, and then you're really connecting to the batteries here. And then essentially what happens is that you're injecting the holes and electrons into this depletion region, and they're recombining and emitting light. As I mentioned to you, there's no cavity here, so that's why the light is randomly distributed. So that's why we call it as an incoherent light. And wide variety of LEDs are now currently being used, for example. So for example, if you want to make red or orange or yellow LEDs, for example, we are using aluminum, gallium, indium phosphide. It's a combination of these materials. Different materials end up emitting different colors of light. And then the blue light was a missing one. And then the gallium nitride and indium gallium nitride technology developed by Japanese scientists, Dr. Nakamura, Dr. Amano, and Dr. Nakasaki, has led to the development of the green LEDs, or now the same materials also by changing the composition. People are using green LEDs as well, for example. This has happened during the last 25 years or so. It's a really an exciting development. That was a missing color because we had the red and then the green, but not the blue. And that means, you need to have the third primary color in order to be able to generate the white light. So here is the case again. You look at the nitride semiconductors, and they talk about the lattice constant, and then the different nitrides and gallium nitride, aluminum nitride, indium nitride. You can see they're all lattice mismatched. And so then again, by essentially alloying these ones, you'll be able to tune the band gap. So that means you're able to tune the emission wavelength of these particular different materials emitting different colors of light, for example. So here's a case where you can make wide variety of blue, red, green LEDs, and that's what the combination of it can lead to the white LEDs. But sometimes people come up with trying to combine all these three colors and be able to get very good light emission means you really make complex things. What people have found is that they can take a blue LED, put some yellow phosphor, that can also create white LED, white light, and that's what people are now currently typically using. So that's why whenever you look at LED lights, some of these ones, if they're used, these three, you can see very bright white light. But sometimes if you see the bluish white, so most likely they might have used a blue LED with the yellow phosphor that ends up creating this bluish white light also. As I mentioned to you earlier, that really the LED lights are really playing an important role. Solid state lighting, it's a tens of billions of dollars of technology now. In fact, nowadays in Australia, for example, and nobody is allowed to sell these incandescent lamps, and you're only allowed to send either compact fluoros or tube lights, which are about 25% efficient, as I told you, or otherwise LED lights mostly. In fact, at my home, and all of them have got only LED lights, for example. That means you're consuming less power, for example. So decorative lighting has become really an important thing. For example, automotive means again the brake lights to the flat, the all sorts of lights now. The people are using LEDs. For example, here people are also using for displays. And for example, most of the times nowadays people are moving towards again TVs, and the indoor lighting and all things are made out of LEDs. Also, people are using LED technology for agriculture, indoor agriculture as well. And people are finding that depending on the change of the wavelength of the LED which you're using, then the yield of the crops which you're really getting and other things are also playing an important role. Really, these are playing an important role there. So of course, indium gallium nitride LEDs, and again, see that these are all LED lights, and so even the stadiums are using the LED lights as well, for example. Here. So Professor Shenoy says that in IIT Delhi campus, apparently they've got all the LED lights now, and all the street lighting and all things been used, and they're really able to reduce the greenhouse gas emissions, and then also reducing the power consumption as well. And these are the three professors, those who developed this nitride technology. But most interestingly, there was no crystals which are really lattice matched to gallium nitride, but these people have been able to show, despite the presence of defects, and these particular materials really emit very bright light. And then that's what led to really demonstration of blue LEDs, led to the 2014 Nobel Prize in Physics. And so really, it's a really exciting development in the field of semiconductors. So now let me move from lasers and LEDs to photodetectors. And then I told you that photodetector again is a PN junction. But in this case, instead of forward biasing and you're reverse biasing these ones, you can see the negative terminal of the battery is connected to the positive side of this diode, and positive side of the battery is connected to the negative side of the terminal. So now you shine light on top of this photodetector, and then essentially you generate photocarriers like electron hole pairs, and then you apply the bias so that you can efficiently be able to extract these carriers as quickly as possible before they start recombining again. So that's a very important one in the case of photodetectors, for example. Of course, you end up creating PN junctions, means you end up having the PN junction. That means essentially what you're doing is that here's a case where the band diagram here which shows P-type semiconductor here and type semiconductor here, and then this is a so-called depletion region where you shine light, and then that's the one which is this depletion. The depletion region also creates a built-in potential that can separate the electron hole pairs. So instead of using a simple PN junction, because the PN junction width is very small here, for example, depletion width is dependent on the dopant concentrations on both ends, but people are moving towards PIN, P-type intrinsic semiconductor, N-type diode. Also, people are exploring avalanche photodiodes and various things. So here is a case where you got a standard PN junction, for example, here. This shows that the electric field distribution in the depletion region, for example, here. And then you got the drift region, and also the diffusion region and various things which I will not have time to talk about. Key thing is that you're shining light and then reverse biasing it, and then be able to extract the carriers. So by introducing the intrinsic layer, what happens is that the volume of the material which you're really shining light increases. So that means you're able to really, be able to really create much more efficient photodiodes and other things, and also that you can also be able to control the junction capacitance by controlling the thickness of this particular intrinsic layer. And then particularly if you want to make a high-speed devices, and reducing the junction capacitance plays an important role, and that's what people end up using these ones, for example. So here is the actual structure, how it looks like. And then again, you try to grow the N-type layer, intrinsic layer, P-type layer. And again, you try to put some anti-reflection coating, so that means you're able to couple the light efficiently, and you'll be able to again contacts and be able to extract the carriers after shining light here. And some more details of this indium phosphide, indium gallium arsenide based photodetectors, which are really used for 1.55 micron and 1.3 micron wavelength regions, which are used for optical fiber communications, for example. And again, use also double heterostructures and other things as well here, and for wide variety of purposes. Again, main purpose is to absorb as much light as possible, and then be able to also separate the carriers efficiently, and also be able to really have got the high-speed devices, because that's where optical networks require those ones. Again, I will not go into the details, and then indium gallium arsenide plays an important role because of the fact that that's a wavelength region which is of interest for communications, for example. And then many groups, including ours, have spent a lot of time. And then Professor Joe Campbell, and so then really as a pioneer in this field, and from University of Virginia, has really developed some of these avalanche photodiodes and wide variety of devices. And essentially, he's dedicated his life in developing a wide variety of photodetectors, and really made a big difference in terms of developing the optical networks and then systems and things like that. What about other semiconductors? And we talked about 2-6 semiconductors, and again, particularly in terms of photodetectors, particularly for defense applications, and we want to be able to really go to longer wavelengths where the atmospheric windows are there, 8 to 14 and 3 to 5 regions, and that's where mercury cadmium telluride plays an important role. And also mercury telluride and cadmium telluride has got a very close lattice matching, so it means by mixing these ones, you'll be able to make wide variety of detectors. In fact, this is a benchmark for any photodetector, and these detectors are used by wide variety of defense companies and also defense agencies, because mercury cadmium telluride are very efficient detectors. And my colleague Professor Laurie Ferroni from University of Western Australia, and of course SSPL and others have played an important role in this area as well. So efficiency of the quantum efficiency of the photodetectors again depends on the number of hole pairs which are generated with respect to the number of incident photons, and then you can really look at the photo generated current as a function of the incident power. And then we call this particular prefactor called as responsivity, and the responsivity is really be able to tell you that how good and how bad is this particular photodetector is. And you can in fact look at these ones, and basically we calculate these ones as amperes for watt, essentially number of amount of current generated with respect to the power of the optical power of this particular light which has been falling on these ones. And really this responsivity really is an important parameter. And also we also look at the noise and other things and detectivity and all these things as well. So you can see that responsivity as a function of wavelength, and silicon is also very good in terms of photodetection point of view. That's one of the reasons that the solar cells and photodetectors and CCD cells are made out of silicon. But again, silicon is very good from about 0.4 or 400 nanometers up to about 1100 nanometers or so, and afterwards it becomes transparent because it's below the band gap of silicon, and that's where the germanium comes in, and then indium gallium arsenide comes in. Indium gallium arsenide is particularly efficient, and that's why the optical communications industry and others are using indium gallium arsenide detectors, and a lot of spectroscopy people are also using in-gas detectors to be able to detect a wide variety. So the silicon is 300 nanometers to 1.1 microns, and the peak, the detection wavelength is about 800 nanometers, and then typical responsivity is about 0.5 amps per amp watt. Germanium is more for 0.7 to 1.8 microns, and peak is about 1.45, and this more responsivity is better. Indium gallium arsenide is even better. It covers the spectrum of the 1 to 1.7 or so. Of course, now with extended in-gas detectors are able to go to 2 microns or so as well. And you can see the responsivity plot as a function of the wavelength here, for example. So, well, anyway, I think I've covered my 1 hour or so. We said that we'll really try to cover this initial topic for an hour or so. And I hope you got some idea of how the semiconductor heterostructures and double heterostructures and different materials are used for making laser diodes operating at various wavelengths, light emitting diodes operating at wavelengths, and also the photodetectors, and how you can make use of these quantum wells by applying electric field to be able to modulate the light. So these wide variety of devices are used for a wide variety of applications. Again, Professor Shanna, I wanted to leave with you, and how do you be able to get into this field of photonics? And then obviously all of you are already doing one degree or the other after year 12. Either you can go to BTech into electronics or electrical engineering, for example, or engineering physics, and then go and do MTech and do a PhD, or otherwise go from BTech directly to PhD if you really perform very well there, or somehow you're not able to get into BTech and you end up going to BSc and do MSc, and then either go to MTech and do PhD or directly go to PhD. And then essentially PhDs in photonics are used by industry, and also the academic organization and R&D organizations and defense organizations and others are also making use of those ones. So there's a lot of potential there in terms of employability if you really gain right kind of skills for in the photonics area, for example. With that, and I'll stop here in terms of that part of it and introductory part of the optoelectronic devices. And then let me now move towards silicon photonics. I've been asked whether can I cover some aspects of the silicon photonics as well. Silicon. I told you till now that silicon is not a very good light emitter. So does that mean that silicon cannot be used for photonics applications? And I've already shown you silicon can already be used for photodetectors, for example. But so generally, silicon, most of the photonics people really try to put silicon down, but reality is that silicon is pretty good in terms of for other applications. And in fact, for example, if you talk about silicon is widely used, this is, by the way, these slides are from Professor Sebastian Rudedas from Royal Institute of Technology in Stockholm. And so basically silicon is, as I mentioned to you, heavily used for electronics applications and CMOS process, about 300 millimeter silicon. There's 12-inch diameter. Silicon is used for a wide variety of means of processors and memory chips and all these things, and very low cost and all things as well. The technology has been developed during the last 50, 60 years or so, for example. But it also turns out you can really create waveguides of silicon dioxide on silicon, and particularly silicon on insulator, for example, and thereby you're able to really create a highly efficient waveguides, for example. And it also turns out that the silicon-based devices could also be used for modulators, which I was talking about, and Intel and others, Michael Lipson from the Columbia University, she used to be in Cornell University earlier, and Roel Bartz at IMEC, and then John Bowers at UC Santa Barbara have really demonstrated a wide variety of optoelectronic devices based on silicon, and also many groups have been working in this area. Though the silicon may not be very good for the light emission applications, but the silicon could be used for modulation and also for in terms of waveguides and multiplexers and demultiplexers and silicon dioxide combination. And most recently, people are also using a lot of silicon nitride as well, and particularly silicon nitride based devices are even showing more lower losses, and this is an exciting development. So really, there are some things which you cannot use silicon. I mentioned to you that indirect band gap semiconductor, that means you cannot use it for light emission, and it's a centrosymmetric, so that means it's not very good for modulators. And but at the same time, what people have done is, and people have really tried to put in fact, Richard Sorev is the one who really demonstrated by changing the carrier concentration in silicon, you can really change the refractive index of the medium, and then be able to use that one for modulation applications or so. And then nowadays, by putting the silicon into a cavity and be able to really allow the light to interact with the medium much more often, and by having high Q cavities, and thereby people are able to show very highly efficient and high speed modulators. In fact, Intel is now manufacturing these ones, for example. Because of this reciprocal nature of the semiconductor, you cannot create isolators and circulators, so that means you cannot really decouple the ingoing light and outgoing light. And that's where what people are looking at is that try to combine silicon with 3-5 semiconductors with optical gain and modulation and absorption, and then try to really combine silicon with some of these yttrium, garnet materials, for example, for isolators, and the magneto-optic materials, essentially isolators and circulators. And people are also trying to combine this lithium niobate, periodically poured lithium niobate, and quasi-phase matched 3-5 semiconductors like gallium phosphide for non-linear optics applications as well. So one can get around these things, but lattice mismatch and others really create some problems of combining 3-5 semiconductors with silicon, and many people are really addressing in various ways in doing that. So silicon photonics is expected to play an important role, particularly silicon, and also silicon on insulator, for example. Is a schematic of the EU roadmap, which has been released more than about 20 years back or so, trying to really combine the various devices. For example, here optical waveguides and optical modulators and optical detectors and spin devices and CMOS devices, and all of them on the same chip, molecular electronics and RF components. Essentially, light is the only one which is missing. And essentially, there's one point of view is that you have an external laser, you really couple that light through the optical fiber, like you're really the coupling the using the external power supply to be able to means power your computer chip. In the same way, you can get the light also from the external source. But people are also exploring this may not be the most efficient. How to integrate the laser diode lasers onto this silicon, so thereby everything is monolithically integrated, for example. There was some discussion about really be able to do this optical interconnects on the chip, for example, because of the fact that if you're going to smaller and smaller dimensions, the resistance of these metallic connections becomes really a major issue. That means it creates problems and creates a lot of heat and other things. People have really talked about trying to really have the optical interconnects on the chip, but still there's a long way to go. But whereas basically board-to-board connections and other things, people are using optical connections, optical interconnects these days. And in fact, lots of supercomputers, data centers, and they're using a lot of optics to be able to really be able to one system to the other by using vertical cavity surface emitting lasers and photodiodes and other wide variety of devices, for example. So why are we interested in silicon photonics? And one of the things is also, for example, internet. And Google search, for example, really consumes about even at the time 1 kilojoules of the amount of energy which has been used, for example. So again, I mean, thing is that really data centers are really consuming huge amounts of electricity, for example. And again, the optical interconnects really can reduce the cost of some of these, reduce the energy demand for these ones, for example. And so really, it's in fact the power consumption of these data centers is much more than annual consumption of some other nations, for example. And again, electrical interconnections and huge energy consumption and signal delays and limited bandwidth and data rates and other things. And that's where optical interconnection, silicon photonics is expected to play an important role. So again, this is details about the data data center energy consumption, and you can see that it keeps on increasing. And people are predicting the Asia Pacific is going to, in fact, be using more and more data. For example, India and China and other, because of a huge amount of population in the Asia Pacific. And then whereas maybe in the North America and other things, the amount of usage may come down and other things. And that means there's a huge amount of power consumption. We cannot continue to use electrical interconnects, and that's where optical connections people are interested. So Intel has already released the 50G, means the silicon photonic links, for example, is a hybrid laser and a modulator and a multiplexer. and then a connector to the sent to the optical fiber cable. And on the other end, you're really doing the demultiplexing and using detectors or so. In fact, these are some of the so-called silicon transmitter receiver systems. And except for the light which is coming from these, these lasers, which are really, really essentially did something called a wafer bonding, and to be able to do these ones, and it's really looking very promising from that point of view. For example, already been used by industry, for example. So in terms of the industrial silicon photonics, and then already people are using for multiplexing and demultiplexing and Mach-Zehnders and optical gyroscopes and wide variety of things people have been really developing, and it's looking very promising. Here's a case where people are exploring there was a pluggable optics and onboard optics and co-packaged optics and 3D co-packaged optics and a wide variety of things people are really exploring, and then be able to really use these ones for a wide variety of applications and co-packaging wide variety of devices on the same chip, and you're able to really be able to get lots of functions of the first generation to second generation to fifth generation. Here you'll be able to really bring the integrated lasers, so that means you can reduce the power consumption, and also the footprint of the devices also can be reduced quite significantly. You can see the dimensions also been shown here. Well, there are a wide variety of needs for means that people have identified, and these are particularly integrated photonic systems roadmap, and which has been identified in June, released in last year, and which has identified a wide variety of technologies which are needed, for example. And then essentially means for some applications you need low chip volume, and that means diamond sizes are not a problem. But for some high chip volume, that means you'll really be able to high functional devices, and you need to be able to take the multiple functional devices, and that's where the dimensions and other things are going to play an important role. I'm not going to go into the details of these ones, but the key message is that silicon photonics is going to play an important role, and while the 3-phase semiconductors and other things are will also continue to play an important role, most likely both will go hand in hand. Currently, the people are predicting about currently the silicon photonics about $1 billion industry, and by 2025, people are really predicting it will be about $3 billion industry or so. It's growing at a very, very fast rate because of the demands from the data centers and high performance computing applications. So of course, light sources, means integration of light sources on silicon. So it means you got electronics and the light in the same system. It makes a big difference. And also that you can be able to create a multi-junction solar cells on silicon by using wide variety of materials. Also ultra-fast optoelectronics and silicon as well. Once you've developed the technology of integration of 3-phase semiconductors in silicon, and you can really start seeing wide variety of applications, for example. So how do we do this one, integration of 3-phase semiconductors on silicon? And then there are three main techniques people use, and so the two main techniques, and one is called as wafer bonding. And then what people end up doing is that really try to bring the silicon wafer and then 3-phase semiconductor wafer, and then they use some sort of a molecular bonding or adhesive bonding or metal belt bonding and transfer printing and wide variety of techniques people use. Another way of doing that is epitaxial growth. That means growing the semiconductors on silicon, and then there are lots of challenges, and the lattice mismatch and other things play an important role. And then using some of the nanostructures, and people are trying to get around that one, for example. So this is the some of the work which has been the so-called evanescent coupling. This is John Bower's group at UC Santa Barbara, who has really pioneered this work and working with Intel group there, and then it really played an important role there. And people have also been looking at hybrid approaches of really trying to combine this ring resonator laser along with this waveguide, and be able to couple the light in and out using this particular waveguide, and with photodetectors, able to take the light here. Polymer bonding is another one, essentially putting some polymer on silicon and putting some polymer on 3-phase semiconductor, and then be able to heat these things up and then bond these two things together. And then metal bonding and polymer bonding and wide variety of technologies people are using, for example. People are also trying to make some micro disc lasers on top of this silicon on insulator. And in fact, this is the work of Dr. Geraldo Hattori, who used to be in my research lab. He's my colleague at University of New South Wales in Canberra now. And then he is in France, and he was working there, and then he was really developing this technology of trying to create micro disc 3-phase semiconductor lasers on silicon, for example, or silicon on insulator. I would not go into the details of these ones, and I was mentioning to you about the dislocations. And what people are finding is that you really open a small nano slot here, and that means what happens is that if you're trying to grow indium phosphide on top of silicon, and then you really create a mask there, and then basically what happens is that these dislocations get terminated there. And if you really create this one very thin area, That means what happens is that this can grow further and then laterally grow, and in the process you're able to get a very good quality in indium phosphide or other semiconductors. For example, this work of Professor Sebastian Rudedas and working with Professor John Bowers and other colleagues there. And you can see that they're able to show that you can get a good quality indium phosphide on silicon and with silicon dioxide masks. And this is called as epitaxial lateral overgrowth. And that they're able to show that you can really get a good quality quantum wells as well. And using this particular technology, for example, it's a very, very complex growth process. It's a non-trivial process, and you need to spend a lot of time. Professor Sebastian Rudedas has been working in this area for about 20 years or so. And then they were able to demonstrate with 1.5 micron multi-quantum well LEDs, not lasers yet, but they are LEDs. And they're able to show that they got a very good transparency, current density, and other things which they're able to demonstrate. As you can see, that higher the amount of current you're injecting, higher the amount of power which you're able to really get. But ultimately, they're able to show the gain, but at the same time, still, they're not able to show that they're lasing yet. And then there's still a lot of challenges. That means there's a lot of cavity losses and other things which are taking place that need to be addressed. So I think with that, I'll stop here. And then really in the first part of the talk for about 1 hour, 20 minutes or so, I've really covered these basics of the optoelectronic devices and also some of the recent developments in silicon photonics and the great opportunities in silicon photonics. I'll stop here and I'm happy to answer any questions you may have. Thank you for your attention. Okay, I'll stop presenting. Hello? Are there any questions? I hope I haven't lost you.
Hello, any question?
So maybe make sure that you unmute yourself when you ask the question, because sometimes you mute and then you don't realize that you're muted and you keep on talking.
Yeah.
Which happens all the time to me.
Yeah, I have one question,
Yeah.
Jagadish.
Yeah, please go ahead, Dr. Gopal.
Yeah. So this quantum dot lasers.
Yeah.
Can you tune it? Because
You're talking about tuning the wavelength. You're talking about, Gopal?
Yeah, tuning the wavelength.
Okay. So the thing is that typically what try to do is that we can really change the composition of the quantum dots and the thickness of the quantum dots such that by choosing the right growth conditions, and we can really make them either operating at a 1.3 or 1.55 microns, and those are the wavelengths which are of most interest for people, and because of our optical communications or so. And so then, of course, you can really modulate them to high frequencies. I think people have even demonstrated directly modulated 25 gigabits per second, room temperature operation and lasers. And in fact, Professor Dieter Bimberg's group at Technical University of Berlin and Professor Arakawa's group in Tokyo University really been able to show that.
Yeah, because the size effect will play a role, because if they change the size, I don't know, that's what I was.
Absolutely, it does play a role. That's where the optimization really comes into picture, and then be able to really choose the right composition, and then be able to really tune that one in the right ways to be able to do that one sort of thing, for example. And so it's a non-trivial process, but by really being able to really tune these things carefully, of course, as you can see, that the strain plays an important role. And then by using the right composition and the tuning of the strain, and then you will really be able to make quantum dots operating at either 1.3 or 1.55 micron. And people have demonstrated, and then we've worked on a wide variety of quantum dots, but we didn't go to those wavelengths, and we really demonstrated, indium arsenide quantum dot lasers and indium gallium arsenide quantum dot lasers, indium arsenide and the indium phosphide quantum dot lasers, and gallium arsenide nitrogen quantum dot lasers, and other things as well.
Oh, thank you.
Thank you. Any further questions?
Hello, sir.
Yeah.
Sir, I have a question.
Go ahead, Sana.
In wide bandgap semiconductor, can we have certain like GaN-based lasers and have used like lateral polarity structure to create a efficient laser?
Absolutely. In fact, gallium nitride lasers are widely used. For example, these days you can get even laser pointers which are made out of gallium nitride, indium gallium nitride system of the blue lasers or even violet lasers or so. In fact, the same materials which are used for making LEDs are also used for lasers as well. And so then, in fact, means nowadays, in fact, people are moving towards the UV lasers because the UV lasers and UV LEDs are really important for, for example, people want really decontamination of the places and also detection of the biomarkers, for example, and if you got some virus or something, how do you be able to detect those ones, and also destroying the DNA of the viruses and other things. Also, people are trying to develop the UV-based LEDs and lasers as well. And so we have been working, and we are working on a boron nitride, hexagonal boron nitride, and also aluminum gallium nitride and other things. There's not been an easy process, and particularly if you're going to high aluminum content, aluminum gallium nitride and other things, there are lots of challenges of the strain and then the cracking of the layers and the doping challenges, and also large amounts of oxygen getting in, and then that's really killing the efficiency of the lasers and the LEDs as well. So then really full spectrum people have demonstrated from the infrared lasers to the UV lasers using aluminum gallium nitride, indium gallium nitride technology.
Okay. Thank you, sir.
Any further questions?
I have one more question. What is the power
Please,
we can achieve with the quantum dot lasers? Maximum power in milliwatts or?
No, but people have really demonstrated even much higher power lasers as well. So what they've done is that they've really stacked multiple quantum well lasers, quantum wells, and be able to enhance the gain volume and be able to do that one. That's where also challenge is try to do this one so that you're really not creating huge amounts of strain. In fact, we have demonstrated by putting some gallium phosphide, for example, and then you really create the strain compensating layers, and then we've shown that the thermal stability of these lasers is much better, particularly while you're doing the top cladding layer and other things, and whenever you put the strain compensating layers and other things as well. People had to play with lots of tricks in order to be able to really get a much higher powers. Any further questions? So it looks like all of you need some tea. Is that right?
Yeah.
Okay.
Absolutely.
So why don't we take maybe 10-minute break? Is that okay?
Yeah, sure.
Okay. We'll take a 10-minute break and we'll come back in 10 minutes.
Yeah, sure.
Okay. Thank you very much. I'll
Thank
see you in 10 minutes, all of you. Thank you.
Sir, shall we start?
Yeah, sure. I'm ready. Whenever you're ready, then we can start. Yeah, sure.
Yeah. Yeah.
What? Want me to start?
Yeah. Gopal, sir, shall we start?
Yeah, we can start.
Okay.
Okay.
Yeah.
Yeah, we are on time. Yeah.
Yes, sir.
Okay.
Thank you.
That's good. Excuse me. Okay. Okay. Welcome back, and then hope you have had a nice break and had a chance to have a cup of tea. And so really, now I'm going to really tell you about our current research and what we're doing in this field. And so really, now, I mean, it's basically this morning again, and I'm going to talk about semiconductor nanowires or nanostructures for optoelectronics and energy and neuroscience applications. So, by the way, that in addition to being working at the ANU, I have honorary appointments in various parts of the world, and I want to thank all of them for inviting me to be associated with their universities. It's really a pleasure to be associated with so many colleagues in various parts of the world. And before I proceed further, and then this research, and this is my own research, and so that means I really want to acknowledge this. Today's talk is really a collaborative effort between my group at the Australian National University and many groups in Australia, US, UK, China, and so Sweden, Italy, Russia, Switzerland. So really, beauty of science is that there are no national boundaries. We can all work together, and then really by working together, we can be able to do more exciting science. And I really want to thank all my collaborators and many students and postdocs, those who contributed to our research. And without their effort, and there's nothing much to talk about, I want to sincerely thank them. And it really has been a pleasure for me to be, working with all of them. And this is my own research group at the Australian National University, and then typically about 10 to 12 nationalities at any one time. And it's a really wonderful group to work with, and again, very bright people. And I want to really sincerely thank them for all their efforts. And again, they are the ones those are really doing all the exciting stuff. I'm going around and giving talks, and I want to really sincerely thank them. And also want to take this opportunity to thank our funding agencies for providing some support and then allowing us to have fun. And then if really we don't get any funding and we cannot really have fun, which is not good for us. So from that point of view, really, I want to thank them for the support which they have provided.
Can you share the slide?
Oh,
Slide
it's
is
not
not.
sharing. Oh, I apologize. Oh, I
No.
apologize. Oh, I
Yeah.
apologize. Oh my God. Okay, sorry. Uh-huh. Okay, I can see myself there, and I was thinking that. So I apologize.
Yeah.
Okay.
You have to go back again. I also
Yeah,
have the
that's
same problem with this Google Meet.
yeah. Google Meet is sort of one of those things.
Not comfortable.
Yeah, somehow it's not as user friendly as
Yeah.
Zoom and others. Can you see the slides?
Yeah. Now it is okay. Now it's okay.
Okay.
Just move like
Let
please.
me see whether it moves or not. That's the next question which I have for
That you
you.
have to check.
Let me see. Okay, is it moving?
Now it's very good. Very good.
Okay, that's good. Okay, so this is a sorry that so basically means I'll be talking about semiconductor nanowires and nanostructures for optoelectronics, energy, and neuroscience applications. Initially, being at the ANU, I have honored appointments in various parts of the world, and I really want to thank all my colleagues in various parts of the world for inviting me to be associated with their institutions, and it's been great pleasure and fun working with my associated with those my colleagues there. As I mentioned, this is a collaborative effort between my group at the Australian National University and many groups in US and UK, China, and Sweden, Italy, Russia, and Switzerland. And so really, science has no national boundaries. We can all work together. And then I certainly enjoy working with all my colleagues. And I've only listed the professors or the senior researchers in those groups, but there are many students and postdocs have been working in those groups. And I want to thank all of them for their contributions, and really working together, really we can be able to make much more exciting science than doing on our own. And then I certainly enjoy, and I'm a strong believer of collaboration and cooperation than competition and conflict. So this is my group at the Australian National University, and typically at means about 10 to 12 nationalities at any one time. And so many people are here. And then Sonacham came from CECRI Pilani, and then Vidur Raj came from Delhi, and Nikita Gagrani came from IIT Kharagpur, Anna Bhatt came from NIT Srinagar, and then Vinny Gautam came from Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore, and Shiva Karaturi came from IIT Madras, and then later on from NTU in Singapore, and so Deepankar Chuk came from Delhi, and Ashwini Gopkumar and came from Kerala. So now you can see that it's a really multidisciplinary group, and also there are many Indians there as well. So, okay. Also, I want to thank many funding agencies for providing our support our research and allowing us to have fun. And really, it's important that without the funding support, we really can't do much. And I want to express my gratitude to them. Here is overview of my talk, and then I'll give you the motivation for our research, and then why we are interested in nanowires and nanostructures, and I'll talk about the growth of these structures, and lasers and LEDs, and the terahertz detectors and modulators, and if I have time, I can cover modulators as well, and solar cells, and photoelectrochemical water splitting using nanowires, and the neuron growth as well, and I'll draw some conclusions. And before I proceed further, and then many groups are working in the field of semiconductor nanowires and nanostructures in various parts of the world. And so really, I want to really thank all of them, because science is really built on others' contributions and we learn from each other. Again, it's important to acknowledge other groups those are working in our fields, and I want to thank all of them for their contributions and enriching our field, for example. So before I proceed further and then talk about nanowires, and let me really talk about technological revolutions. As you know, that the first technological revolution started with the steam power and mechanization, led to mechanization, and second, the industrial revolution started with electrical power and then mass production, and third industrial revolution started with computer power and automation, and in the fourth industrial revolution, people are predicting that the biological world and the digital world will come together, and then the light is going to play an important role to be able to interface humans and machines, because 80 to 90% of the information which we receive is through light. So really, light-based technologies are going to play a very important role. And also, currently the light-based technologies are about 1 trillion Australian dollars, and so that people are predicting that it will be doubling by 2030 or so, indicating that there's a lot of potential for growth, a lot of opportunities for contributions as well. So in terms of the World Economic Forum has recently identified what the technologies needed for the future. And then they've identified holographic displays, and then wearable optical sensors, and then also light navigation and communication using things like LiDAR, and a 3D vision and gesture recognition, enhanced machine vision, and augmented reality. And really, all these technologies require smart miniaturized systems, and that's what we're really trying to develop as part of our new Center of Excellence funded by the Australian Research Council, Center of Excellence on Transformative Meta-Optical Systems, TMOS. Okay. In this center, what we're doing is that we are really trying to make use of the nanostructures for the generation of light using nanostructures, manipulation of light like meta-optics and other things for manipulation of light using meta-optical structures, and then also the detection of light using nanostructures, and to be able to create active meta-optics. A lot of meta-optical devices are available in the more of a passive type, and we want to be able to do the active meta-optical systems. And this particular Center of Excellence has been directed by my young colleague, and Professor Dragomir Neshev, and then he's leading the center. And this center is also for 7 years or so. So there are about 5 universities in Australia is involved in this center, and then about 15 CIs are involved in the center, and really covering a broad spectrum from materials to optics to optoelectronics to device engineering to including packaging and a wide variety of technologies. It's really an exciting time for us, and it only started in the beginning of the year. And then recently we filled the PhD positions and postdoc positions, and then we keep on advertising the future positions at this website. Please keep an eye on this one and then apply for those ones as and when the vacancies arise. So now let me move towards optoelectronics. And we've already covered this one. And then we said that optoelectronics is essentially conversion of electricity into light for LEDs and lasers, and then conversion of electricity into light for photodetectors and solar cells, for example, and which led to the developments in these areas has led to large area displays and the solid state lighting and infrared imaging and the night vision, and including in manufacturing, and then also the solar cells with the high efficiencies. But we've also talked about the optical internet and then how optoelectronic devices are playing an important role, and mainly the 3-5 semiconductors are used. And in fact, that is the one which I'm going to really mainly focus on. And that's also focus our research as well. So nanowires. Nanowires are seen as building blocks for the next generation electronics and photonics. And so one of the unique things with the nanowires is the lattice mismatch is no longer an issue in principle. You got a material which got a large lattice constant with respect to a substrate. It can expand without creating dislocations. You got the material which got a small lattice constant without which can contract without creating dislocations. So in principle, you'll be able to make nanowires of any material on any substrate without the constraints of lattice mismatch, which I talked about in the previous talk of the introductory talk earlier. You can also use this, grow the actual heterostructures like quantum dots or quantum disks within the nanowire. For example, this green material is different than the red material. You can also dope these nanowires to be able to p-type and n-type so that you can make p-n junctions, for example. Also, you can create a radial heterostructure nanowires or a core shell nanowires. This red material is different than the pink material, for example. Also, you can get the branch nanowires as well. So really, in fact, these are some of the examples from my own laboratory where we have shown you can grow gallium antimonide on top of gallium arsenide. Despite large lattice mismatch, you're able to really grow atomically perfect gallium antimonide on top of gallium arsenide. Gallium arsenide, as I mentioned earlier, is a very good infrared detector material, for example. Indium arsenide is a very good material with a large carrier mobility, which is very good not only for infrared detectors, but also for high-speed electronics as well. And we were able to show that you can grow indium arsenide on top of gallium arsenide. You see this branch of indium arsenide on top of gallium arsenide, which could be used as cantilevers and scanning probes and other things. We've also grown indium phosphide nanotrees, and these nanotrees could be very good for energy harvesting applications like the splitting of water to generate hydrogen, because hydrogen economy is going to play an important role because hydrogen is a storable and transportable and a clean energy source as well. And most recently, we're moving from nanowires to nanomembranes. And then again, really, this is opening up a lot of opportunities for us, and I'll come back and then talk to you about that. So most importantly, international technology roadmap for semiconductors, and these are the guys who are determining what technologies are needed for the next generation electronics. They've identified the nanowires are also a key technology component for electronics. And because the lattice mismatch is no longer an issue, in fact, people are now trying to grow indium gallium arsenide nanowires on top of silicon. For example, IBM Zurich, and have really demonstrated on a 6-inch silicon wafer indium gallium arsenide nanowire-based transistors, and they've shown excellent performance from these ones, which is looking promising. So the nanowires could be useful for making lasers and LEDs and photodetectors, biosensors, and solar cells, as well as for electronics like transistors and high-speed transistors or so. So if the nanowires are so much of interesting, and so they've got a lot of potential, how do you make these nanowires? There are two main techniques which we use. One is called as a metal catalyzed VLS growth process. Another technique is called selective area epitaxy. And we use a technique called metal organic chemical deposition, MOCVD. There's an alternative technique called molecular beam epitaxy, MBE. You can use either of the techniques depending on your own choice, and we happen to have MOCVD reactors, and then we really try to use those ones for growth of these nanowires. So in the case of metal catalyzed VLS growth process, we typically take nanoparticles of gold, for example. In this case, I'm showing an example of 50 nanometer gold nanoparticles. These things comes in a colloidal solution. You put a droplet of that one there. And then it turns out the gold has got a melting temperature of more than 1000 degrees Celsius. But once if the gold starts reacting with the gallium or aluminum or indium, then what happens is that the eutectic forms. That means, alloy has got a much lower melting temperature than the individual component melting temperatures. For example, most of these alloys of gold gallium, gold indium, and gold aluminum has got a melting temperature of about 350 degrees Celsius. So then if you put this one into the MOCVD reactor, heat it up to put on gallium arsenide substrate, for example, put this in an MOCVD reactor, heat it up to somewhere between 370 to 500 degrees Celsius, and then you're creating this gold gallium eutectic liquid, and introduce the gases needed for the growth of gallium arsenide, for example, trimethyl gallium and the arsine. These gases get incorporated into this liquid alloy, it gets supersaturated, and then they get precipitating out. And you always see the gold nanoparticles on the top, and then you can see that, and the gallium arsenide is precipitating out of this nanoparticle, for example, here. Here is a case of the gallium arsenide nanowires. In fact, this is the work of Dr. Hannah Joyce, and during her PhD at the ANU in my group, but now she's a professor, an associate professor and a reader in Cambridge University in electrical engineering department there. She's demonstrated that you can really get atomically perfect cylindrically shaped nanowires. Till that point, she developed a technique called two temperature growth process. Essentially, to summarize it, she starts the growth at a high temperature, and then after nucleation, she reduces the growth so it avoids the lateral growth, thereby, instead of creating tapered nanowires, and then you're able to get a beautiful cylindrically shaped nanowires, which are important for laser cavities and other things. But also that when we looked at the transmission electron microscope image of these nanowires, we found that absolutely no defects, no twin defects and other things which you normally see, and you get atomically perfect nanowires. And showing that we're able to really show these gallium arsenide nanowires, 50 nanometer diameter. You can see the gold nanoparticle is sitting on the top. Essentially, you can make the nanowires of as small as 20 nanometers we have done, and up to 300 nanometers, essentially changing the diameter of the gold nanoparticle which you're using. So really, depending on the what applications you have, you choose the right diameter of these nanowires, and which I'll come back and then share with you what type of diameters are needed for solar cells and lasers and others. So in the case of the selective epitaxy, we don't use any metals, and we deposit some silicon dioxide using plasma-enhanced chemical electrophoration, and then put some photoresist, a Z photoresist, for example, do electron beam lithography, create patterns of holes, for example. You transfer these patterns through SiO2, and then you expose the indium phosphide in these holes here. Put this one in the MOCVD reactor, heat up somewhere between 650 to 750 degrees Celsius, and introduces the gases needed for the growth of indium phosphide, in this case of trimethyl indium and phosphine. These gases dissociate, and then the nanowire starts growing, for example, here. You can see this nice, beautiful structure here. These ordered patterns of these indium phosphide nanowires, beautiful hexagonal facets, and then these nanowires are growing in the 111 orientation because that's the lowest surface energy orientation. We typically use 111 substrates in order to be able to do that. This is the work of Dr. Chian Gao. Now she's at Blue Glass in Sydney, working as a research engineer, trying to make LEDs and glass, for example. Again, in this case, we have made nanowires as small as 70 nanometers, as big as 700 nanometers. So we can really use either of the techniques to be able to make any of the 3-5 semiconductors. And depending on what applications you have and then what is the purpose of these nanowires, we choose a particular technique which we want to use, and then try to produce a good quality nanowires, for example. So then we gone off and looked at the light emission from these structures, and then we excited these nanowires with a laser pulse to generate electron hole pairs, and look at the light coming out of those ones, so-called photoluminescence. And you can see that the quantum efficiency of the light emission from these indium phosphide nanowires, the red curve, is very much comparable to indium phosphide epitaxial layers, indicating that the surface recombination do not play an important role in the case of indium phosphide, and also that we're able to get excellent quality indium phosphide nanowires, enabling us to be able to get excellent quality efficient solar cells, as nanowires in this particular case. These are very good for making lasers and solar cells and a range of things, for example. So we asked ourselves, instead of opening a hole, what will happen if you open a slot in the silicon dioxide mask, or otherwise a ring? This is the work of my student, Dr. Nain Wong, and he's joining us as a postdoctoral fellow. We just finished his PhD. And then again, we take indium phosphide, put some silicon dioxide or silicon nitride, put some photoresist here, do electron beam lithography, open up of either slot or a ring, for example, and then put it in the MOCVD reactor and then try to grow these nanostructures. And of course, Nain Wong has spent about 4 years in optimizing wide variety of conditions, growth conditions, in order to be able to get good quality structures. So here is a case where when Nain Wong opens the slot along a particular crystallographic orientation of 101 bar, and then puts it into an MOCVD reactor and heat it up to somewhere at 680 degrees Celsius, introduce the gases needed for the growth of indium phosphide, you can get these beautiful nanomembranes here, for example. But if you open the slot along another crystallographic orientation of 112 bar, and then you get also the membranes, but these membranes are thicker, but they've got a different facet than this particular one here, for example. If you open the slot in between these two orientations, what you end up creating is a beautiful diamond-like structures with these alternating facets of this particular one and this particular one, for example, here. So now you can see, instead of just making nanowires, we're able to really make nano membranes and nano diamonds and a wide variety of structures. So then we have gone off and then opened the ring, for example. Again, Nain Wong has spent a lot of time in optimizing these things. And then once if you really open the ring, you can see also these with this alternating facets, you get a beautiful rings-like structure here. If you keep on growing, in the middle also it gets filled up. And then ultimately you end up finishing off with this nice, beautiful, hexagonally faceted the nanomembrane, which is very good for nanomembrane lasers and MEMS applications and a range of applications. So really, as you can see, that not only nanowires and wide variety of nanostructures which are growing is really opening up opportunities for us to be able to really explore for wide variety of applications. And in fact, we've gone off and looked at the light emission from these structures. You can see that nanomembranes and the nanodiamonds and nano rings from the top view in the electron microscope image. And here is a cathode luminescence image, because cathode luminescence is something which we do in an electron microscope. You excite the nanostructures with the electron beam rather than a laser pulse, and then you generate electron hole pairs and look at the light coming out of these ones. You can see that the beautiful bright light emission, very light uniform light emission, indicating that Nayan Wang's hard work of 4 years really paid off. You're able to get a very good light emission and very uniform, indicating that they are defect free and things like that. But in fact, most recently, my new student Wei Wong has recently demonstrated ring resonator lasers, because we can make use of these rings for ring resonator lasers and other things. That paper has just been published in Nanoletters, for example, just gone up on the web just now. So now we move from materials to devices, lasers. And we just finished talking about lasers, and we said that we need to have a gain medium, you need to have a laser cavity, you need to have mirrors, and then you pump the gain medium to create population inversion, as and when the model gain is equivalent to the optical losses, and then you start getting the lasing, for example. This is called as a so-called transparency condition, and once if you above that, then you start getting lasing light coming out of these ones. So also there's an equation which is essentially saying the same thing. The gain should be equal to the internal absorption losses and mirror losses, and then only the lasing starts taking place. So it turns out if you take a nanowire, if you shine light from the top, then what happens is that the light is coming from the both ends of the nanowire, because nanowire acts like a waveguide. And then also both ends of the nanowire act like mirrors, as I was mentioning to you. Is that nanowire has got a refractive index of 3.4, and then the air has got a refractive index of 1. That refractive index difference creates mirrors. So that means nanowire being a direct band gap semiconductor, it's already got a gain, because that's what you would expect. And then the both ends of the nanowire has got like mirrors. That means in principle, each nanowire should act like a laser. If I get the design right and I get the good quality nanowires or so. So that's what we spend a lot of time in trying to optimize these things in order to be able to explore and then be able to make some of these nanowire lasers, for example. So really, we've been working in this area for quite some time, more than a decade or so. And in fact, we demonstrated a wide variety of nanowire lasers. And Dr. Drew Saxena, who is now at Imperial College, has demonstrated the world's first gallium arsenide nanowire lasers in 2013. Dr. Chian Gao has demonstrated the Woodside indium phosphide nanowire lasers. And then later on, with Dr. Drew Saxena has also demonstrated these quantum well, multi-quantum well nanowire lasers. And Dr. Tim Burgess, who is at IP Australia now, has demonstrated zinc-doped gallium arsenide nanowire lasers. But I'll not have time to talk about all of them. I'm just going to share with you one or two lasers. And here's a case where Drew Saxena has been doing simulations of looking at FTDD simulations, finite difference time domain simulations, of electromagnetic simulations, essentially how the light propagates through these nanowires, and then how the various optical modes are propagating through these nanowires, for example. Here's an example of the TM01 mode, which is propagating with a 260 nanometer gallium arsenide nanowire. And you can see the field intensity is the highest at the core of this particular nanowire, for example. If you go for T01 mode, for example, if you make the quantum wells, they look form like a donut, and then we end up really designing these lasers for the T01 mode emission or so. It depends on what particular mode which you really want to have, and you design the appropriately, for example. So here's a case where Drew Saxena has plotted a threshold gain for lasing as a function of the nanowire diameter for nanowire of about 10 microns long. So you can see that this threshold gain is very much dependent on the diameter of the nanowire, also dependent on the optical mode, which is really propagating these ones. You can see that the diameter of the nanowire around 250 to 300 nanometers has got the lowest threshold gain. In fact, I'm not plotting from 0 here. You can see that the smaller the diameter of the nanowires and the threshold power for gain for lasing is so high, then what happens is that you end up having they're burning these nanowires, damaging these nanowires before you can get any lasing taking place. So that's why the designing really plays an important role. Simulations play an important role. Again, Drew has plotted the peak gain as a function of the injected carrier density. And again, this threshold-like behavior, which I was showing you earlier. and which is again threshold. The carrier density needed is very much dependent on the temperature of the device as well. That's what you would expect. And again, in that lecture, we talked about that one, for example. So then, to cut the long story short, and based on the design of Drew Saxena, and then Dr. Nain Jiang, and then Jenny Jiang is now, she's at Cambridge University as a postdoctoral fellow. She has grown these gallium arsenide, aluminum gallium arsenide core shell nanowires about 6 microns long, and then Drew Saxena transfer them onto glass slides and pump them with a laser pulse and look at the light coming out of these ones. You can see that this below threshold, you see a very broad light emission, like a spontaneous emission, like a light emitting diode. And then above threshold, you see a very sharp light emission, like a stimulated emission, for example. And you also see that the interference fringes showing that these are going to laser, a coherent light emission is coming out. And you can also see that Drew Saxena has simulated one with the measured the devices, and they're very much comparable with the simulations, the interference fringes he's measuring here also. Here is the output versus pump intensity, again threshold-like behavior. The log-log plot showing the S-type behavior. This part is the spontaneous emission, this part is the amplified spontaneous emission, and this part is the one where you end up getting the lasing taking place here, for example. Okay. So in fact, these are the first gallium arsenide nanowire lasers operating at room temperature, which we published this work, and it created a lot of excitement in the community. And just to give an idea, these nanowire lasers are about 6 microns long. So that means I can put about 20 nanowire lasers in the width of your hair. That really tells you these are some of the smallest lasers in the world. Smaller the laser, they consume less energy. Smaller the laser, you can switch it on and off faster. Also, you can be able to pack more lasers next to each other or so for various applications. So that's why people are really exploring these kind of small lasers, for example. So then this is a collaborative work with Professor Martin Dawson's group in University of Strathclyde. And then when I gave a talk, and he came and said that they developed a technique called nanoscale transfer printing, and are we interested in collaborating? So that's what we have done. And then what they do is that they come up with a PDMS stamp, and then of course they spent a lot of time in designing the what kind of PDF stamp you need to design and all these things, and develop this technique. And then they can come and pick up this nanowire, and then we can drop it wherever you want. Precise nanoscale location of these nanowire lasers, for example, or nanowires. Again, research fellow in Professor Martin Dawson's group, Dr. Benhua Gulhaber, has spent a lot of time in optimizing and developing this particular technique. I want to thank him, and also Professor Antonio Hurtado and Professor Michael Stein as well. So here is a case where these nanowires, which are really transferred onto glass substrates, flexible glass, because we want to use them for flexible optoelectronics applications. You can see these nanowires which are on here in the optical microscope here. And then you pump these ones and look at the light emission. You can see that the light is coming from the both ends of the nanowire. And then also you can see threshold-like behavior, very sharp light emission, and indicating that you can really get this transfer process, a gentle process. And by the way, these are indium phosphide nanowire lasers. And then you can also get a beautiful light emission, indicating that this is really very good technique, and we'll be able to now precisely locate these nanowires wherever you want. So then we asked them, can you be able to locate these nanowires in front of the waveguide? In fact, they have done that one. And they've really created these SU8 waveguides, put these nanowires, and be able to couple the light through the waveguide. But say, for example, for multiplexing and demultiplexing applications, where they're able to show that the light has been propagating, and then you're able to measure the light here. And again, there's a PhD student, Dimitar's Geotics work in this particular one sort of thing. Again, he spent a lot of time in optimizing these things. So then we asked them, can you locate these nanowires into nano antennas? So this is the work of my young colleague, Professor Fang Ren. Now she's at Nanjing University. She spent some time in my group. She has been making this something called terahertz metamaterials with these nano antennas of the aluminum here, which she calls them as a bullseye antennas. And in these antennas, there was a gap in the middle. So then we asked them, can you locate these nanowires in this gap in these nano antennas here? You can see they're able to locate these ones most of the time. You can see the close-up of this particular one here. So now if you excite this nanowire and you look at the light emission, but if you do not have any nano antenna, you get the light emission from the both ends of the nanowire, because nanowire acting like a fabricated cavity, which we talked about. But whereas if you got this nano antenna, light gets engineered, and then you're getting suddenly the light from the vertical direction. So now you can see, again, this work we published about 2+ years back. And again, you can see threshold-like behavior, sharp light emission, and now vertical emitting nanowire lasers. These are the world's first vertical emitting nanowire lasers. Again, it created a lot of excitement in the community here. So now, if you want to couple the light to an optical waveguide, and I'll give you an edge emitting laser, and if you really want to use it for the facial recognition or holographic displays and all these things, we can be able to provide you these vertical emitting nanowire lasers. And also in that case, you can be able to create two-dimensional ordered patterns, which could be used for meta optics applications and a range of things that are really looking very exciting from that point of view. So till now, I've only shown you the nanowires which are grown by, which are optically pumped. And these are not electrically pumped, but ultimately industry wants to have electrically pumped nanowire lasers. Till now, we have demonstrated by designing carefully and then also by optimizing the growth conditions of various nanowires, we're able to demonstrate optically pumped nanowire lasers. So if you want to make an LED laser, for example, you need to do the doping, and we talked about earlier that the P-type indium phosphide. There's a work of Dr. In-Suk Yang, and he came from Samsung. Now he's gone back to Samsung he's working as a research engineer there. And then he doped this indium phosphide at the P-type part of the nanowire, and grown this indium gallium arsenide, which is quantum well, and then he put the N-type indium phosphide on the top there. Again, he spent about 2 years optimizing these things. And again, I want to really thank all my students and postdocs and also my collaborator students and postdocs. They might have spent a year or 2 or sometimes 3 years in order to be able to get these beautiful results. And that's why I sincerely want to thank them. So then he transferred these nanowires onto a glass slide and then tried to make contacts using electron beam lithography, gold titanium contacts, and then injects the current and look at the light coming out of these ones. You can see the IB characteristics is showing like a diode-like behavior, indicating that he's able to be successful in making ohmic contacts or so. So now we are injecting the current and looking at the light coming out of these ones. You can see higher the amount of current you're injecting and higher the amount of light coming out of these ones. You see 2 emission peaks and at 1.3, 1.55 microns. The reason for having 2 peaks is the quantum well, which is going on the top of the nanowire, this axial quantum well has got a different thickness and composition than the lateral quantum well, which is grown on the nanowire, which has got a different thickness and composition. So that's why I end up having 2 different emission peaks. It turns out that those emission wavelengths are very good for optical communications applications, for example. You can see the light output versus injected current. You can see that there's no threshold-like behavior. Essentially, there's no narrowing of the line width as well. So indicating that these are acting like lasers rather than light emitting diodes, for example. So this is the challenge is you ask the question why are not able to make lasers? But it turns out that whenever you put metals on top of these nanowires, these metals have got optical losses because metals absorb laser light, for example. So that means you're creating a lossy cavity. So to get over these losses, you have to pump them harder. You are pumping them harder. You're creating a lot of heat, and in the process, means you're reducing the gain peak. And that means you have to pump them even harder. It becomes like a vicious circle. So now we got a new student, Nikita Gagrani, who's from IIT Kharagpur, and she has been spending last 4 years or so really trying to replace these metals and replacing them with indium tin oxide and aluminum doped zinc oxide and other materials, with the hope that she's able to really inject current and still be able to minimize the amount of losses so that we can get injected lasers. Still, she was able to make LEDs till now, and she's still trying to really make an effort to get these many things to laser. It's been a really challenging project, but she's working on it, and I hope by end of the year or beginning of next year or so, hopefully we'll be able to make electric injected nanowire lasers. Before In-Suk finishing, instead of using a single nanowire LEDs, and then he really tried to really make array LEDs, and you can see these nanowires which are grown, and then the challenge is how to make contacts. You can really fill this one with the polymer material, selectively etch a polymer material, plasma etching, and put some indium tin oxide, and put some metal contact at the top and the bottom. So inject the current and then look at the light coming out of these ones. You can see the IV characteristics showing that the diode-like behavior. And again, as and when you're injecting more and more current, you're getting the more and more light emission coming out of these ones, for example. So indicating that these, particularly because you're embedding them in a polymer material, you can peel these things off, and that means you can use them as a flexible LEDs. That means they're particularly useful. For example, Samsung and Apple and others are interested in foldable phones and foldable computers and other things. And that's why these could be very useful. And in fact, that's why In-Suk has spent a lot of time in optimizing these things, for example. So from LEDs and lasers, now let me move towards terahertz radiation. So we all know that electronics, we have gone from microwaves and RF to the millimeter waves. And also in optics, we have gone for photonics, we have gone from ultraviolet to the visible to the infrared region. There was a gap called terahertz gap for a long time. In the last 20-25 years, people have developed technologies, including us, of making terahertz sources and detectors and a wide variety of things. Why are we interested in terahertz radiation? It turns out many of the chemical molecules have got signatures in the terahertz parts of the electromagnetic spectrum, and the lactose and monohydrate and anhydrate. And so they really, you can see that they can night signatures. This is a terahertz parts of spectrum. So in fact, many of the chemical molecules, like for example, drugs which are manufactured by the pharmaceutical companies, are even explosives. And so they have got terahertz part of the electromagnetic spectrum. So that's why defense and security people and chemical are biological people, and many people are interested in terahertz radiation. But also terahertz radiation can reflect is reflected by metals, for example. So that means, nowadays, for example, at the airports, when you go to this round box, and then they don't use X-rays anymore, because X-rays are ionizing radiation. They create damage to the DNA. Use non-ionizing radiation like terahertz radiation, and terahertz radiation really allows you to be able to detect the metal parts and other things, sort of thing. And that means you're not creating also damage to the DNA. You can also use it for biomedical applications like detection of cancer or detection of cavities in the teeth as well. And then also wireless communications, where you can download information onto your smart devices from a kiosk without having to have any metal, the wire contacts or anything of that sort. Also, you can use it for the water content determination in leaves. So thereby, farmers will only be needing to water the plants, crops whenever they need to. Thereby, you're able to preserve the precious resource like water, for example. This work on terahertz work is both on sources and detectors has been mainly jointly with Professor Michael Johnston, Professor Laura Hertz's group at Oxford University, and this is the work of my student Kun Pang. And then during her PhD, now she's a postdoctoral fellow in Oxford University. During her PhD, she tried to develop these nanowire-based terahertz detectors. So what Kun Pang has done is that she has taken these nanowires and transformed them into a quartz substrate, because quartz is transparent terahertz radiation, and put some metal contacts. And so thereby you're able to really shine light and then excite this one with a laser pulse, and then create electron hole pairs, come up with a terahertz pulse. Electric field of the terahertz pulse is separating the carriers between the two contacts. You measure photocurrent as a function of time. So that really opens up opportunities for you to be able to really measure photocurrent as a function. You see the time scales we are talking about is picoseconds. They're very good for terahertz applications, for example, terahertz detection. If you measure the current as a function of time, you can measure the electric field of the terahertz transient as a photoconductive detector, for example. Also, you can measure the time-dependent photoconductivity of the detection material as well. So in fact, initially, we started using this terahertz technology to be able to measure the non-contact way of measuring the conductivity and mobility of the carriers in these nanowires. And that's where we got this idea, instead of using ensembles of nanowires, can we use a single nanowire and be able to make terahertz? Again, to cut the long story short, and yes, in fact, during her PhD, Kun Pang has demonstrated gallium arsenide nanowire terahertz detectors, indium phosphide nanowire terahertz detectors, and then she's shown that the antennas which are used play an important role. She's been using Bauta antennas in order to be able to really create this broad bandwidth, amplitude, and phase sensitive room temperature operating terahertz detectors. And most recently, during her postdoctoral fellowship at Oxford, jointly between us and then Oxford University and Strathclyde University, she's recently developed this so-called polarization resolved terahertz detector. So in this case, instead of using a 1 or 2 nanowires here, and then she tries to have the nanowires in both 90 degrees to each other. So you can see the close-up of this one here. These are the Bauta antennas, and then here's the nanowires. And the challenge has been to avoid contact between the top nanowires and the bottom nanowires. So really need to she spent about 3 years in optimizing these things to avoid that ones, otherwise they'll be shorting. And then she used these ones to be able to measure the performance of these particular detectors. And then what she has done is that she has developed this so-called design, the terahertz metamaterials. And then we come up with the terahertz pulse, and then terahertz pulse is interacting with the terahertz metamaterial, and then it changes the polarization, and use our detector to be able to measure the X and Y polarization of the modified terahertz pulse. So now we can see that these are the ones which are freshly fabricated or based on the design. And you can see the terahertz transmission for the X polarization you would expect this way. Y polarization you should be like this, as theoretical simulations show, and our experimental results show very similar response, indicating that these really terahertz polarization sensitive terahertz detectors are very useful. to be able to simultaneously measure both X and Y polarizations or horizontal or vertical polarizations, to be able to fully characterize the performance of this. For example, terahertz metamaterials or so. Again, these are the room temperature operating, polarization, and amplitude and phase sensitive terahertz detectors. And this work last year has been published in Science, and again, it creates a lot of excitement within the community. Then this is the work with my former student and now Associate Professor Dr. Anna Joyce group at Cambridge University, and Professor Michael Johnson, Professor Laura Hedges group at Oxford University, and our group at the NU. Instead of using the nanowires in a 1 nanowire, and then Laura, Hannah's students have really tried to really serve it big, has really embedded these nanowires into parallel in C and also in an aligned way. So now if I really come up with the laser pulse, if the polarization of the laser is aligned to the nanowire and it gets absorbed and then it generates photocarriers, and then next you come with the terahertz pulse, it's interacting with the carriers and it gets modulated or reduced from amplitude, for example. If the polarization is perpendicular to this one and it don't get absorbed that efficiently, in the process the modulation is not that high. So this joint work with Sarwat Beg and Jessica Boland, who is now a lecturer in Sarwat is working in a company, and Jessica is working in University of Manchester as a lecturer there. So you can see that again, to cut the long story short, and that this on-off ratio of this polarizers as a function of the polarization angle, and you can see that largest amount of polarization is taking place 0 degrees, indicating that that's where the absorption is taking place, and then essentially also, of course, dependent on the laser power as well. And at 90 degrees, you expect it to have small modulation. That's what we have seen. Also, these are the broad bandwidth terahertz modulators, and so we're able to show that they're also high-speed modulators. They could be very useful for terahertz line of sight communications and other things. You need to be able to modulate to send information and other things, and really it's an exciting development as well. Again, all these are also operating at room temperature. So now let me move towards nanowire solar cells. So as all of us studied about solar cells, and then we studied that we need to have a p-n junction, and you need to have a thick enough material to absorb all the light, and you shine light and generate photocarriers, and these carriers need to migrate long distances from the top and the bottom, and you lose some of the carriers. For example, if you say that the solar cell is about 20% efficient, and then 80% of the carriers have been lost to defects or impurities or surfaces. And so, but in this case of nanowires, you can make the nanowire as long as you want to absorb the light. You can make a p-n junction, lateral p-n junction. That means you get a p-type core, for example, or n-type shell, or the other way around. So thereby, the light can be absorbed this way. The carriers collected in 90 degrees way. So it means you're able to efficiently collect the carriers, and they are essentially decoupling light absorption pathways and carrier collection pathways. Because of the high refractive index of the nanowires, they also act like light funnels, and the light gets concentrated into the nanowire, and that's where you need to order these nanowires carefully. Also, they got low reflection losses, and again, that means you don't need to put in anti-reflection coatings and all. Again, we've done lots of simulations, and so Dr. Sudha Makapati, who is now an associate professor at Monash University, is involved in this particular work, and she working with students, and we're able to look at what should be the diameter of the nanowire, what should be the distance between the nanowires, or the pitch of the nanowires, and also what should be the height of the nanowires and various things. As you can see, that the most of the current is generated at the tip of the nanowire, indicating that you don't need to make very long nanowires, and these gallium arsenide or indium phosphide 1 or 2 micron long nanowires are more than sufficient to be able to really collect most of the current, for example. We also looked at the diameter of the nanowire and diameter to pitch ratio. As you can see that for these ones, the diameter should be somewhere between 150, 160 nanometers. Diameter to pitch ratio should be around 0.5 or 0.6 or so. Okay. You can see that as a function of this, the short circuit current as a function of the diameter to pitch ratio, that's what we're indicating here. So again, based on these simulations, and my students have grown these structures, and then you can see that the gallium arsenide, aluminum gallium arsenide structures, and the schematic of this one here, the actual sample here, fill this with a BCB polymer and selectively plasma etch this one and expose the tips, put some indium tin oxide at the top and then the metal contacts at the bottom, and then shine light and look at the light emission, look at the efficiency of the solar cells, for example, the current generated. Again, to cut the long story short, and then these are some of the examples of my colleagues from Technical University of Eindhoven and the FOAM Institute, Professor Eric Barkers and Professor Rick Garnett. they've demonstrated some of the most efficient nanowire solar cells, which are about 17.8% efficiency, which is looking extremely promising. And we've been working with Laura Hertz's group at Oxford University, and we're able to show that by instead of using BCB or other polymers, how about using organic semiconductors, which are very good for a whole transport, but not very good for electron transport. We can make use of the combination of these things so that we can also peel these things off. So that means they can be used as a flexible nanowire hybrid in organic solar cells. And that means in the future, we'll be able to really provide you these solar cells, which are really be able to attach to your backpacks and other things so that they'll be able to charge your smartphones and other things very efficiently. And that's what our goal and that's what we're working towards. So now let me move to another topic of the water splitting to generate hydrogen. And we know that if we can really split water into hydrogen and oxygen and be able to collect hydrogen, hydrogen, as I mentioned, is a clean energy source, and also that we can transport it and store it, unlike solar cells, and where you can only generate it during daytime. That means storage is an issue which we need to always worry about, charging batteries or one thing or the other, for example. And the transport also, the hydrogen probably much more easier, particularly long distance and also heavy haul and other things. So in this case, essentially what you're doing is that you take a cathode, and which could be a metal like platinum, and then a photoanode, which is a semiconductor, and then essentially you shine light on top of this photoanode, generate photocarriers, electron hole pairs, and then holes will go and oxidize water in order to be able to create oxygen and then protons, and then the electrons from here goes to this side here, and then really interacting with the protons and to be able to reducing protons to be able to make hydrogen, for example. So typically to have this reaction to be working, and then at least the energy which you need is 1.23, but generally you also got some losses in the system and other things, and typically you have to have about 1.6 electron volts or so in order to be able to really make these things to work. And again, this work is led by my colleagues, Dr. Shiva Karaturi and Professor Hotan, for example. So in fact, we've looked at a wide variety of materials. In fact, this is a slide which I borrowed from Professor Jiten Me from Michigan University. And then they've looked at a wide variety of materials, and typically chemists end up using titanium dioxide. And you can see that one of the requirements is that the band gap, there's a conduction band and a valence band here. The band gap of this semiconductor is such that the redox potentials of the water should be in the middle of the band gap here. So you can see that there are some semiconductors they can do that one, but the challenge is the gallium nitride is very good. You can do that, but gallium nitride doesn't absorb the visible light. We only absorb the UV light. But whereas indium nitride only really straddles one of these potentials. So, but if you go for indium gallium nitride, so which can have the smaller band gap, which is good for absorbing the visible light, also straddling the redox potentials of water, which can really be a very good material from that point of view. So based on that one, we've looked at the gallium nitride, and this is the work of my student, former student, Dr. Reddy, and also Dr. Liu from engineering. And then Reddy has really made these gallium nitride nanorods, and then really coated this with the cobalt oxide as a co-catalyst and also stabilizer. And then by using cobalt oxide, he's able to show that you can really get a stable performance from these gallium nitride nanorods. Normally, gallium nitride is very difficult to etch chemically. You have to use plasma etching. But whereas in the photooxidation or photocatalysis conditions, still the photocorrosion takes place because of the accumulation of holes. By putting cobalt oxide, and also acting like a co-catalyst, also scavenging the holes, so thereby be able to get a very stable performance from these structures. But gallium nitride, as I said, is not the best material. We are exploring things like indium phosphide nanowires and indium gallium nitride nanowires and other things in order to be able to really use them for be able to make efficient the energy harvesting devices like generating hydrogen, for example. So most recently, we demonstrated a combination of perovskite solar cells and silicon photocathodes, and in collaboration with our colleagues at Professor Kylie Katchko's group in engineering. And then by using this perovskite, which really provides the energy needed to be able to really run this one, is a standalone solar water splitting system, and where we were able to demonstrate 17% efficiency. And in fact, Cool and Earth Forum, which has identified this is one of the top 10 innovations in 2020 for climate change and energy change mitigations. So it's really nice to see that our work has been acknowledged by the broader community. Let me finish off with the last topic of brain repair. This work of Dr. Vinny Gautam, and she did her PhD from Jawaharlal Nehru Center in Bangalore. Now she's a lecturer. She spent some time in my group, and now she's a lecturer in biomedical engineering at the University of Melbourne. while she was at ANU, Winnie has looked at these, how to really create a brain repair, for example. You know that all of us have got about 80 billion neurons, and then they form into neuronal network. So whenever you got a brain damage, for whatever reason, whether you got an accident or otherwise due to dementia or one thing or the other, and then you end up creating this breakage of these neural networks, and you lose some of the functions. You cannot talk or move or one thing or the other. But whereas if we asked ourselves, can we create a neural patch and be able to make the connections back? And then so thereby you'll be able to help people with neurological disorders, for example. Of course, it's a long-term goal of this one. So Winnie has spent about 3 years in optimizing these various protocols and trying to get the medium right and other things. She tried to grow these neurons, which is a cell body soma here, and these neuroids are really following these nanowires very nicely. These are the indium phosphide nanowires on which she has been growing these ones. Also, you can look at some of the dendrites coming out of these axons and other things as well. Instead of using a single neuronal cell, what will happen if you use a multiple neuronal cells? And so it turns out that when you have these ones, and you can see that the box is the one where you got these neuronal cells, and you can see she has grown the multiple neuronal cells, and you can see that these really the neurites and the axons and others are following these patterns beautifully. And on the planar surface of indium phosphide, the neurons are also there. You can see that they're making some random connections also. So we've done this calcium dye imaging, and then what Winnie does is she puts some calcium dye, and then as and when the action potentials have been fired by these neurons, ion channels are opened up, calcium ions passes through those ones, and then the fluorescent intensity dependent on the number of the calcium ions are available there, and then she really takes a video of this one and try to create correlation maps. If this neuron is firing, what's happening to this neuron and this neuron and this neuron and these astrocytes and other things, and try to correlate to see, is there any cross communication is taking place between the neurons or not? Again, see, Winnie compares these ones which are grown on the glass substrates and then the indium phosphide nanowires. As you can see that the first one, the glass substrates, is a change in fluorescence as a function of time. You can see that there's different neurons are firing at different times. There's very little correlation, and correlation shows very, very small when you really try to look at this communication between the neurons. But when we grow these neurons on indium phosphide substrates, you see the change in fluorescence as a function of time, and they're all firing at the same time, indicating that there's some sort of a synchronized and correlated activity is taking place, and a lot of correlation coefficient looks excellent from that point of view. When Winnie presented this work at neuroscience conference 3 years back or so, they were asking her what type of neurons you're using. They were quite excited about this one. So then she said that she's using rat neurons, and they said, why are you wasting your time with rat neurons? How about using stem cells? So now we got a project funded by Dementia Research, Australia Research Foundation and Ilgilbar Foundation, and where we're able to work with colleagues of the neuroscience, stem cell biologists, neurobiologists, and then computer scientists or artificial intelligence experts and nanotechnologists, all of us together, and taking the neurons from the stem cells from the Alzheimer's patients and healthy people, and then create these organoids or the mini brains with and without microglia, and doing the microelectrode analysis and calcium imaging, and using deep neural networks to be able to analyze the data, and so that we're able to really understand and then develop which particular neurons, how they respond for the drugs and various things. Again, we are also developing some new nanoelectrodes, and this is the work of Dr. Vidar Raj, and then where we're able to really use those ones, develop these ones so that we want to measure single neuronal cell data, so that we can get a much better understanding of how these neurons are functioning, and what are the differences between Alzheimer's neurons and healthy people, with the hope we'll be able to help the people with Alzheimer's disease. So this is an exciting project. I have very limited, I'm learning a lot because of the fact that I know very little about neuroscience and stem cell biology, or so. It's been great fun. With that, let me draw some conclusions. Nanowires open up opportunities for manipulation of light matter interaction at the nanoscale, and developing the new class of lasers and LEDs, Faraday detectors and modulators, integration of optoelectronic devices on various platforms, and developing using nanowires for solar cells and PEC water splitting, and engineering the growth of the neuronal networks. Finally, let me leave you with some information. As has been mentioned, that Applied Physics Reviews is a really high impact journal, and we are accepting original research and high impact original research, as well as also high impact reviews. And it's got an impact factor of 17.05. And then if you got some breakthrough results, or you want to really write an exciting review, please get in touch with us. And also that our Center of Excellence, please keep an eye on this website, And then also there's an opportunity to work in 5 different universities. Again, that's why we may not have vacancy at the moment, but other universities may have vacancies. Keep an eye on that one. And my wife Vidya and I have really created an endowment and at ANU to be able to support students and young physicists coming from the developing countries to come and spend about 3 months. So which also led to our College of Science starting a Future Research Challenge program. In 2019, we had about 52 students came from India, one student came from Indonesia, and they really had a great time working with my colleagues in astronomy, biology, chemistry, earth sciences, medical sciences, and also physics and science communications. But unfortunately, in 2020, we could not bring anybody because of the fact that we had COVID, and again, 2021 probably will not be able to do that one as well. Again, this is something to give back to the community because we both feel we have been really, because of the various teachers and parents and others have supported us in our careers, and we want to express our gratitude to them. With that, I want to thank you for your attention, and I'm happy to answer any questions you may have.
Yeah. Thank you very much, sir, for your wonderful talk and so much of information you have shared. So there is one question which has been posted in the chat box. Can these photoelectrochemical cells be used to generate oxygen or hydrogen from air in atmosphere in the future?
Some of the challenges are that potentially you could probably create some plasma and then be able to split the air. But the problem is that air has got not only just oxygen. Probably the amount of hydrogen in the air is not as high in terms of concentration. So it means you have to spend huge amounts of effort in order to be able to extract hydrogen. But whereas the water is, of course, means a significant of hydrogen is there. That's why people are focusing on water splitting to generate hydrogen. But also, people are also exploring other things as well. For example, the same process could also be used for conversion of CO2 for say for generation of methanol and other valuable chemicals as well. So there's another way of reusing the CO2 to be able to usable things, and that makes sounds like a closed cycle as well. A similar process may be used in this one. And people also want to generate things like ammonia, for example, which can be a transportable fuel and other things as well. So these photoelectrochemical systems have been developed and used for a wide variety of applications, and water splitting is only one of them.
What are the challenges in using nanowire solar cells in charging smartphones?
Okay, that's a very good question, Dr. Gopal. And then, so basically, at the moment, the challenge is that means the efficiency is about 17% or so. There are also small areas which are able to do that one. But the challenge is that means make sure that these flexible solar cells are really be able to really withstand lots of means flexing. Means that those are the experiments which have not been done. How stable these flexible solar cells are and other things. And again, these early stages of development. There's a lot of work need to be done now to be able to make these flexible the solar cells made out of nanowires. We've also been exploring the planar solar cells, also flexible solar cells using spalling techniques and other things so that you can make thin gallium arsenide solar cells as well. But the thing is, the advantage of nanowires is that the nanowires really have got to use a very small amount of material. Also, nanowires are very efficient to grow because in a very small amount of time, you can go through a few micron nanowires. So that means you really don't have to spend huge amounts of time in trying to make the epitaxial layers and other things. And that's where the advantage is. And there's still a long way to go, in all honesty, in order to be able to make these things to work well once. And of course, there need to be interfacing and all these things. One need to electronic side also you need to worry about as well. And also that if on a cloudy day, how much of energy you're able to generate and how long it will take to be able to charge these devices and all other logistical issues one need to think about. At this stage, we are focusing on the conceptual issues and then see what are the limitations technologically we can, in order to be able to achieve our goal. It's a good question, and there's a long way to go in terms of being able to use them for real world applications.
So there are no more questions. If anyone has any question, you can unmute yourself and ask.
I think I have one more question. This,
please go ahead,
Jagadish. This nanowire bias laser is interesting, definitely. Now, is it already in the packaging stage? This nanowire based lasers?
So the nanowire-based lasers are also still again the early stages of development, and then of course, as I mentioned to you, they're all in the optically pumped lasers. But if you really want to use them for real-world applications, and we need to make electrically pumped lasers, and that's been our major challenge. And having said that, nanowire LEDs have been used quite widely, and in fact, is a company called Glow, which has been funded by the Google and others. And in fact, recently some other company also already acquired them, and they're able to make these gallium nitride and indium gallium nitride based nanowire LEDs. And because of the fact that the light extraction efficiency is much better for nanowire based structures, and also be able to make the flexible LEDs and for displays and other things as well. And so that's why there's a lot of interest out there as well. But lasers point of view, still there's a lot of work need to be done to be able to make sure we can be able to make reliable electrically injected lasers. Then we'll be thinking about packaging and other things.
Yeah, exactly. Because the perception is that when you talk about, you'll always think about a semiconductor-based kind of packaging, where it's a beautiful junction formed, and then the facets are there, then packaged. For nanowires, it really may be challenging.
Yeah, no, it is indeed, and in fact, that's where again the turns out that when you're looking at the emitting lasers, then it's very difficult to even measure these things. And then what we do is that we put these in under microscope, and then whatever the light leaking out from the ends is sufficient to be able to collect, and then that also represents what is coming from the ends as well. And that's where coupling these nanowires to some waveguides and other things may allow you to be able to really measure the powers and all these things as well. So those are some of those things which we're exploring as well. So still a lot of work need to be done. Let me put it that way.
Sure.
So from the research point of view, that's a good thing. And but of course, technology point of view, I think there's still a lot of challenges which we need to address before you could be able to do that. By the way, I've given also my email address, and if any of you are feeling shy to ask questions, and if you want to send me an email, feel free to do that one. I'm happy to answer any questions you may have. That way I posted it in the chat. And there is also another question is that I think Gautam Hegde was asking the question, what's the reason for using lateral p-n junction nanowire solar cells? Okay, that's a good question. So see, whenever I'm making the axial nanowire solar p-n junctions, for example, there's no advantage. That means the carriers still need to migrate long distances to the top of the nanowire to be collected. So that means you're not really, it's like very much like similar to that of a thin film solar cell, for example. But of course, it's got some advantages of acting like a light funnel, and then also anti-reflection properties and other things. But whereas if you make a lateral p-n junction, that means you can make the nanowire as long as you want to absorb all the light. And then because the p-n junction is only, this is within tens of nanometers, the carriers need to be, can be collected. So that means, you don't lose as many carriers. So that means, you'll be able to get much more efficient solar cells. But by the way, all the solar cells which I've shown you to date, they're all axial p-n junctions, not lateral p-n junctions. There's still a lot of challenges there, because how do you really make these ones, and how to make selective contacts for the p-type and n-type and other things, and that's something which you're also exploring and working as well. So really, there are bad news is that still we are not ready to really offer you any devices based on nanowires other than the nanowire LEDs, which are really have been they're at least closer to the commercialization. But whereas other nanowires, probably sensors also were pretty good, but other lasers and the solar cells and other things, still a lot of work need to be done. A lot of technological challenges need to be addressed in order to be able to make these things to a viable and a reproducible and reliable technology. Any further questions or comments? So most likely you may be hungry, and it's time to forgo and have lunch, right? So of course, always, of course, lunch always comes first. Science always second. But please enjoy your lunch. Thank you very much again for inviting me to participate in this important session. And then, I've enjoyed talking to all of you, and I hope it's been useful for you as well. Thanks a lot.
Thank you. We'll be in touch. Jagadish,
sure.
maybe.
Okay, good. Thank you, Gopal. Thank you. See, take care. Bye bye.
Thank you.
Yeah,
bye-bye.
thank you.
Thank you, Sunil and everybody, and Revati and Suresh and everybody, and hello to T. Srinivas as well.
Yeah.
Thank you, Professor Jagadish.
See you. Thank you.
Yeah.
First question,